Auto-Nulling. And on the left side, you can see the Lorentz transmission electron zero magnetic field, and it doesn't form anti-skyrmions. It turns out that the structure forms instead a helical structure, and the helices are oriented along two crystal directions, which favor block domain walls in this anti-skyrmion structure. And so on the left, you can see these black and white lines. These correspond to magnetization pointing to the right and to the left in the plane of this and so particles a heat. Of the Dirizinski area vector exchange that favors position. Then if you look here in the bottom, we've highlighted three regions within this micrograph, A, B, and C, with three different thicknesses. And in the bottom, you can see a series of micrographs starting from large outer plane magnetic field, 0.27 Tesla, where in A, B, and C, skyrmions are not observed. There's a uniform magnetization. And as the field is successively reduced from the left to the right, you can see at intermediate fields, you can see the arrays of anti-skyrmions, and eventually small magnetic fields, you see the
Hello. You are muted.
Hello, ma'am.
Yeah, good morning.
Good morning, ma'am.
Akanksha?
Yes, ma'am.
Okay, so I'm going to share my screen. Let me know if you can see my screen.
Okay, sure, ma'am.
I get a message which says ICEE 2020 will stop sharing content as soon as you start sharing. So then I start, so your sharing automatically will be stopped.
Pardon, ma'am, I could not hear you
See,
properly.
right now you are sharing a slide, which is IEEE 2020, right?
Oh, this is, ma'am, actually, I am not sharing. It is the by default slide open to all the halls. So
Okay.
it'll start as soon as 11 o'clock is the timing. So it'll automatically get removed by 11 o'clock, I guess.
Okay, so then, but I want to just to make sure you are able to see my screen. So I share right now, and again I will unshare.
Okay, let me see how can that happen. Let me talk to the.
No, that is okay. Let me try. It may actually work. Let me try to share my screen.
Sure, ma'am. Go ahead.
Okay, can you see
Yes,
my slides?
yes. I can see the slide.
So then I can unshare right now.
No problem.
Okay, so I
Yes,
stopped.
that.
Fine.
Okay, ma'am.
Okay, so I will remain online.
Okay, ma'am.
Hello, madam. Hello, Mariam, madam. Are you able to hear me? Hello.
Hello, good morning. Hi,
Hello,
Ankur.
hello, madam. Hello,
Good
madam.
to
How are
see
you?
you. Fine,
Thank
thank
you,
you.
ma'am.
How do you do?
Good, ma'am. I'm good. How are you?
Okay. Fine, thank you. So you are quite pretty involved in ICE, right?
Yes, ma'am. This track actually, I'm handling this track.
Okay, good. So you are track chair.
Yes, ma'am. So,
Okay, nice.
madam, actually, this plenary talk is going on right now.
Okay,
So, I think once that will be finished, I think that time only people will move to other tracks. I think
sure.
because
Okay.
so I think I hope it will finish on time, but maybe I think one or two more it's here and there. So I'm keeping track of that
No
plenary
problem.
talk.
I will be online. I will remain
Yes,
online.
yes, ma'am. So
Yeah, you can.
yes, ma'am. As soon as it completes, then I will inform ma'am about to
Okay,
you.
okay, okay. Thank you.
स्पीकर चेक करने की कोशिश कर सकते हैं क्या? अभी तो वीडियो ऑफ रखा है मैंने, ये स्टार्ट हो गया है। मुझे आवाज तो दे रही है अपना, और कुछ नहीं ना?
So yeah, Shraddha, you are audible completely.
ओह सॉरी सर।
No problem. Hello, Professor Mayan.
Hello, Ankur.
Hello.
I was not
Yeah,
sure if something is running. That's why I did not unmute myself.
No problem. Actually, Madam has already joined, but that time this plenary talk was going on. So I think it's better to get that finished. So that is over now. So, yeah, maybe in 5 minutes we will start.
Yeah, hi, Mayank. Good to see you.
Hello. Yeah, I cannot see you. Good to hear you.
Now you can see me.
Yeah, I can see you.
Okay, good. Nice to see both of you.
Thank you, ma'am.
Yeah, same here.
Yeah. So is plenary talk over?
Yes, ma'am. It's just over. So maybe we can wait for 6 more minutes.
Sure.
Um,
Anyway, I remain online.
Yes, ma'am. Hello, madam. Hello, madam. Hello. Hello, Professor Mariam.
Hello, Ankur? Yeah, Professor Ankur, I'm talking.
Hello, Professor Mariam. I think we can start now. People will
Sure.
join later on because in starting they will be kind of struggling with the software. So,
Yes, sure.
so let me start the session. I'm very happy to invite Professor Mariam Shojaei Bhagini for the invited talk. So the title of the talk is Modular Sensor Interfacing and Signal Conditioning. And a brief biodata of Professor Mariam is Mariam Madam is a professor in electrical engineering at IIT Bombay. She is a Tata Trust Chair Professor in Frugal Engineering and Fellow of INAE. Her research and experience areas include sensors, circuits and system design, development, test, fabrication, prototyping, field deployment, and translation research. Professor Mariam has also expertise in the design of analog mixed signal and RF integrated circuits. She has published more than 270 peer-reviewed international journals and conference papers with her team of students and researchers. She's inventor and or co-inventor of 11 granted Indian patents and US patents and joint recipients of 13 awards. She was also my PhD supervisor. So I'm very happy to invite Madam for this invited talk. So without taking much time, I will just hand over to Mariam, madam. Madam, can
Yes.
you please continue?
Yes, sure. Thanks, Professor Ankur, for the introduction, and it's my pleasure to see now Professor Ankur is the faculty in IIT Delhi and then one of the chairs for the Icee conference. Also, my pleasure to be invited as an invited speaker. So today I want to give you a glimpse of some of the activities which can define what we can do in the area of sensor circuits and systems, and develop something which will be definitely useful and gives you confidence that a lot can be done with all this new young potentials and many graduates and startup activities and opportunities. So that is the main motivation behind just sample works that I want to show you. And of course, details will be provided are provided already in the published papers, but therefore I don't get into much into details because of shortage of time and diversity of the audience. But I will give you the examples so that will help you. So I will turn off my video and then I will share my screen with you. So let me know if you see my screen.
Yes, ma'am, we are able to see the screen.
Okay, great. And you may tell me when I stop, otherwise I may just continue talking. But I'm kidding, I try to keep track of time. And by the way, I have also one option for the backup plan in case there is a network issue. I will use the second connection, so there might be some interrupt in case it happens. Okay, let's start. So you are all familiar, I believe that all audience, about the growth of sensor systems. It's a new area, not very new, but with different modes of applications and available variety of technologies these days and connection to IoT. It's really, this area is growing very fast. And there are tremendous applications, tremendous ways of making these sensors and systems, depending how accurate you want to have them and then how you want to use them and what kind of even lifetime you expect from them. So there are various references, of course, you can look into, but just as one example, you can look at this website, which gives you always updates about the sensor systems. azosensors.com. And I don't read really slides. You can actually read them. But I want just to be quick in moving along with the flow of the presentation, which gives you the different aspects of the research, which can be done, novel research and novel prototyping, which can be achieved well here in India. And of course, you know that the sensor systems are linked to IoT and IoE. In fact, the driving force behind that is actually IoT and IoE, where eventually we would be able not to be present in a location where we want to get information or we want to control a system or we want even to repair or treat a system. So some sensors are very simple, and then I show you some of these simple sensors. By the way, I think this, this window is covering the slide. Okay, so some sensors are very simple to make, and then still have a lot of applications. And these sensors are relatively cheap, so that you don't need really to be worried about if their lifetime is short. So there is trade-off. And why we are talking about that? Because we are talking about applications which are more individual oriented rather than, entity oriented. Research and product development has gone into a phase that really individual human being is considered as a final customer rather than a scientific equipment which is used in a lab. So we are not really looking at that. IoT, IoE, of course, may cover the wide range, but what makes really a lot of opportunity available with limited resources is to look at something which could be individual centric. So now if you look, when you have a sensor, you have various types of modules, or you need various types of modules to get information from this sensor. Sensor, at the end of the day, converts one type of physical quantity into electrical signals. So, but you cannot use it directly. So therefore, you need to have modules to do that. These modules start with some interfacing, and we can call it sensing circuit. This is a kind of interface which sits between the sensor and the actual instrumentation. Then you have a signal conditioning module, and this signal conditioning module really extracts the information in the current form from sensor and makes it ready for digitization. This digitization could be very exact, could be not necessarily very exact. It could just give you information which is good enough for you. So, and then finally, give it to the link which is with IoT and IoE provisions. And on top of that, you need always to think of a kind of power management and energy provision for this for these modules. And interestingly, here, the energy source is becoming one of the considerations. So we cannot consider that electricity is available everywhere. So therefore, these modules come together. So you have heard a lot about these modules, and I'm sure that you have seen many products in the market already available. One of the points that I have noticed is it's not the way that you want always, you will get what you want. The main reason is there are many of them which are defined or eventually produced for some range of applications which are considered the mainstream applications and requirements. But as this sensing and IoT, IoE grows, diversity of the requirements also increases. We need to use this opportunity, and we can, to actually look at the design and developments which are novel, which could be quick, which could give us even a kind of new area for training engineers to be able to design and enhance the available or from scratch designs, and then develop prototypes very quickly and use them. So this is not a replacement, this is like an add-on. And then later on, they become a kind of, IPs, they become a kind of individual plug and play modules. And then you can imagine that you have a library of them, and this library could be actually a real hardware library. And this is something which is very much required. IoT, IoE needs to have really a fresh look into the hardware and the system and the way that it can be indigenously designed and developed. And specifically for applications and problems we are looking at with respect to the Indian scenario. So these systems, of course, could be completely using off-the-shelf components, COTS, commercial off-the-shelf, or it could be ASIC solutions. So both are fine, and both would have their own value. But what we need to have is that to be able to design them to be adjustable and to be compatible or adaptable to the requirements with respect to the dynamic range, with respect to non-idealities, and with respect to the energy consumption, because they may be used anywhere, anytime, and at any conditions. And this is the way it defines the diversity. Now let's give you examples. These examples are examples which are eventually carried out and achieved by PhD scholars. And They are simple, but at the same time, sometimes also not very simple, but they give you a glimpse of what can be done and what kind of potentials are available. Let's look at a simple capacitive sensor. But this capacitive sensor may be leaky. Leaky in the sense that if you want to make a capacitive sensor which is relatively cheap and easy to make with limited resources with respect to the fabrication infrastructure and platform, you may not get a good capacitive sensor. So it may be leaky, it will have leakage current, eventually it gives you a kind of resistive pad, to speak in a simple way. So how we can make a simple C to V converter for simple capacitive sensors, right? And here the example is using commercial off-the-shelf ICs. So nothing special that you say that, okay, we need it. No, we don't need. You don't need any very special arrangement. You just need to get the components. Just purchase the components. Fabrication itself is simple. This is one example of the sensors that we had, and it's too easy to make, and it doesn't need a very sophisticated infrastructure. Therefore, this sensor will be cheap, but of course, it's a leaky capacitive sensor. So I have provided the reference paper for every example I give, and then you can go into details of that later on. But what I want to connect here is how these simple sensors also can be handled with relatively reasonably easy to make signal conditioning, and then you will have eventually everything on your own. So how flexibility is created. So let's look at this interdigited capacitive sensor, which is leaky. So it doesn't give you really a very nice pure capacitor. In fact, everything starts from simple models. So if you look at the model of this leaky capacitor, it looks like something the way I have shown in this figure. So it is eventually showing some effective resistance, showing some parasitic capacitors, but actual information is only included in delta C. Delta C is variation of the capacitor due to some external factor, which could be pressure, which could be change in the dielectric constant of the media, or anything else. So therefore, now we want to see how to handle these issues. So there are some simple principles which are deducted from, which are induced from this simple model. So that's why I want you to see how you can start from simple platform and then build upon that. If you want to get rid of these parasitic capacitors, that means you should definitely have an arrangement where these nodes will be taken care by some voltages, which could be constant at some stage of the measurement. And then to get rid of this resistor, you need to have some kind of information which is only dependent on the imaginary part of this impedance. So these are the simple first principles which will come into the mind of the engineer how to proceed. So now, here one example. So again, I'm emphasizing these are all made using off-the-shelf components, therefore it's easy for you to make it. So now which principle is followed? One of the interesting principles which helps in really getting information from sensors and convert them to other forms. Here we want to convert to a simple voltage from a variable capacitor, is to use a technique which is called auto-nulling. Eventually, instead of measuring a value directly, you actually try to make a particular voltage zero. Here, we have something which is similar to a Wheatstone bridge, a little more complicated, and the leaky sensor is kept over here. And then we use a reference capacitor Cs, of which the value is already known, well measured, as a reference. And then we want to use a kind of closed loop feedback. This closed loop feedback will settle at a particular point when we have almost zero error. And that's why integrator plays a vital role in the feedback loop. And then we have a low pass filter. use a quadrature phase generator to make sure that only imaginary part information will affect the output. And its output is low pass filter. So that means only we need the almost low frequency, very low frequency, close to DC information. So this is a simple modulation which is performed and eventually like a multiplication, which will give you the information in the frequency domain. It's like modulation. It will give you like down converter or up converter. So this is like a converter, which will give you two frequency conversion, low frequency close to DC and higher frequency, which will be filtered by this simple low pass filter. Now, when you use auto-nulling, what will happen is output of this low pass filter will approach to zero in a steady state. That means that the loop now is in completely null mode. And when it is in null mode, the output of the integrator approaches to a constant value, and therefore loop settles. This constant value depends on the voltage that we sense, depends on the reference capacitor, and depends on the K, which is the factor which is used in this multiplier. So details of the derivations are given in this paper that we have published, but what I want to tell you is that how this auto-nulling technique itself can open many avenues to make precise auto-nulling. And you know, this is auto-nulling. You don't need really manually to change anything and give you the information that you need. So it's also very important to know that how to make this quadrature phase generator. You may use an external commercially available quadrature phase generator, or you will make it. And it's interesting, if you want to make it, that itself again can be made using a similar concept. So now this loop itself again uses the auto-nulling. So this auto-nulling is used even to generate quadrature phase generator. So this is very, very interesting work, and it's only using commercial off-the-shelf ICs. Now, applying it to some application. For example, here the main application was water level measurement. Now you can see the board which is made over here, and this is completely this auto-nulling approach. And the effective capacitance, which is really relatively compatible with the actual requirement, is something between 10 to 25 picofarad. And the relative error measurement is something which is between less than 4%. In fact, if you move go to below 20 picofarad, so it reduces below 3%. So it's close to 2% maximum. And you know, 2% error may not be too much when you look into the actual measurement. And then if you limit the range further, so we would be able to get even better lower relative error, which is shown over here. So this is an application where you have a leaky capacitor, which eventually, if you tell anybody that we have made a leaky capacitor sensor, they will say that, okay, it's of no use. So this is to show that you can make a use of it, and that definitely will be useful. So it's not that you will not be able to use it. And this even is compatible with the similar approaches which use commercial off-the-shelf components. Why I'm emphasizing on that? Because when you design an AC, you have a lot of freedom. I'm not saying that, of course, full freedom, but still your freedom is more than the way you use commercial off-the-shelf ICs, because you can adjust supply level, you can adjust the power level, you can adjust the specifications, frequency range, you can do whatever you want because it's a design from transistor level. But when you use commercial off-the-shelf components, you cannot do that. And therefore, you will not be able to really achieve what you need. It's very important to see what you can do with commercially off-the-shelf ICs. And if you look at the last row, the green color row, which is the work reported here. So you can see the leakage resistance can change from 100 kilo ohm to 10 mega ohm. over a wide range of capacitor, which is 47 to 7 nanofarad, which is tunable as well as programmable, because we can just simply change the reference capacitor CS. So therefore, summary is that it is always possible to use auto-nulling as one way of making reasonable, practical, novel circuits for converting one output of the sensor, one form of the output of the sensors to a readable form. For example, when we convert it to an analog voltage, this analog voltage now is available. It can be directly used, it can be converted to digital form, it can be any manner it can be used in the system. So therefore, it's very important to have everything also automated, so no manual intervention. And therefore, it can take care of the leakage compensation, because the way we define it, it only looks at the imaginary part. Relative accuracy is fine. It is acceptable for many applications, including what I mentioned. Power consumption depends, of course, on the type of commercial component you use. It's not very much under our control. But what if we look at the other dimension? Other dimension is, what if we go to the signal conditioning with high accuracy, for example, better than 100 ppm, which was the target for us. In this case, we are talking about resistive sensors. And then here we need to look at, again, non-idealities. Here is opposite way. If you have resistive sensors, then what would be the effect of parasitic capacitors? And if you want to have very high accuracy, 100 ppm, which is much better than what I presented right now, but what I presented right now is okay for many applications. But what we show here is the other side. When we need high accuracy, then here we need to make a compromise. Here we cannot really rely only, of course, we can have the two techniques combined, which could be the future work. But right now, each one of them has its own focus area. So therefore, here we make a compromise. We cannot really handle a very high parasitic capacitor. For example, here on the right side, you see a plot which says that if I want to measure, say, delta R by R of 1 ppm, around 1 ppm, how results will get affected if I change the frequency of operation. Okay, so here we have a frequency of operation for resistive measurement that I will tell you. So as we increase the frequency from, say, 10 radian per second to 1 kiloradian per second, relative error increases from 0.01% to almost more than 50%, which is huge. So that means that one way of handling the very precise resistive sensing is to work at very low frequency, extremely low frequency. So here, for example, 10 radian per second. So what is the meaning of that? Why are we talking about that? Suppose you want to measure a resistive sensor, and then you want to have a reference, same as what we had for the capacitive sensor. But there are parasitic, there we had a reference capacitor, here we have a reference resistor, and there are capacitors. So we have to reduce frequency to a very low value. What is this frequency? This frequency is eventually AC signal, which is applied to these resistors to create a kind of AC excitation. AC excitation is very useful in noise reduction. So you can even call it chopping or up conversion, down conversion. And then after this chopping or up conversion, you can down convert with another multiplication. So this is just like what happens in mixers, receivers and transmitters and receivers, wireless. So you up convert using a mixer, you down convert using another mixer in the receiver. So if we want to do that, then we need to work with a very low frequency. But what would be the problem? The problem with operating at very low frequency is that we cannot get advantage of noise reduction. We need to have really a high modulation frequency to reduce the noise. And these sketches are just showing the concept of modulation. This is just like up conversion and down conversion, and then how noise can be up converted and information can be individually down converted. So Details of the technique can be read from this paper, but what I want to tell you is that if we want to take care of the parasitic capacitance, we have to reduce frequency. If we reduce frequency, we will lose the advantage of the chopping technique or mixing technique, which will allow us to upconvert the noise spectrum, specifically flicker noise, which is very important for resistive sensors. So this how to take care of this high and low eventually trade-off. We need high frequency modulation. At the same time, we need low frequency modulation. One is because we have to reduce the effect of leakage, not leakage, parasitic capacitors, and one is to reduce the effect of noise. So effectively, we have noise error trade-off. Now, what we did in this technique is, as I told you, when we work at the ASIC level, we have a lot of freedom. So what we did is that we actually made two frequencies. We have not two frequency for modulation. One frequency which is low at the sensor side and one frequency which is high at the instrumentation side. And of course, you may say that now we need more choppers or more mixers, which is true. But what another novelty that we did is that to just combine these two using a combiner. And this combiner was a simple exclusive or logic gate. So by going with this high frequency and low frequency combination for the modulation, we have been able to reduce the noise floor of the flicker noise by a very high factor. As you can see on the left side, for the conventional methods, it's around 200, and we are able to reduce it to better than 25, means less than 25. And the frequencies, you can see what we have used. 100 hertz, which is very low, but another high frequency, which is 10 kilohertz. So this way, we have solved the problem. So now, what are the INS or instrumentation amplifier that we have used over here? So we have used current mode INA, which has advantage with respect to trio op-amp base and capacitive feedback INA. And this is the details of the implementation with those mixers that you can see. These are eventually switches, 4 switches. But it's very interesting that we have embedded them within INA, and we have embedded them also within the current source generator because we need to have low frequency modulation for the sensor. And this is the final diagram of the whole system. As you can see, we actually reduced the choppers that we had at the system level, at the INA level, to 2 only by using the XOR. Eventually, we did some kind of mixing of the 2 frequencies so that we applied them directly at the output. And this was another novel aspect with a simple solution. And then we have a 4-stage process which eventually gives a differential and ratiometric operation which measures only delta R by R. So what is considered over here is the mismatch effect. Then we have also considered the offset. We have considered finally the way that we are able to use this ratiometric and difference in 4-phase measurements so that all errors due to the mismatches, for example, small delta R, small delta I, will be removed. Even the base resistance, which is RS effect, will be removed because this is a ratiometric measurement. This whole system, again, is automated. It automatically finds the absolute range for the reference resistor. It automatically adjusts the value of the RF, and then after adjustment, it also adjusts the value of the amplitude of the current for base sensitivity, all within this feedback loop. And based on that, we have been able to achieve the sensitivity, which is better than 100 ppm for the measurement. So this is, of course, the ASIC implementation. And this is the board which is used for the prototyping. You can see the ASIC. Eventually, we have 1 ADC on the board, 1 microcontroller, and 1 power management module. And that makes the whole system. which is very similar, to the modules that I showed you in the block diagram. At the end of the day, you need only them. And this system has been used with a real sensor that our collaborator from Michigan University had fabricated, and we have been able to show the results with a commercial LCR meter, how they match with respect to delta R by R measurement. So this is another dimension that really new and still modular. Why I say modular? Because you can look at this as an IP. This IP is fully automated. It gives you a range of delta R by R measurement. It takes care of the parasitic capacitors, and it is eventually custom-based design. Even if tomorrow you want to change some characteristics, it's all in our hand. So we can just simply change it and then refabricate and make a new ASIC out of it. And then it can go even simply, we have made it in 180 nanometer. It is transferable to SCL technology. So therefore it could give completely indigenized solution. And the characteristics really compete with the existing solutions, specifically with respect to the achievable resolution and sensitivity, which can be made for a wide range of resistive sensors. So we have a wide range. So dynamic range and sensitivity, come together in one solution, and it's fully automated again. So therefore, user doesn't have any issue of handling, a lot of things around that. You don't need to have. And then conclusion here is, it is always possible to bring this high resolution and wide dynamic range with complete auto calibration and in a differential ratiometric solution, and achieve reasonably high accuracy. And this is again in a kind of indigenous design. It is novel, and at the same time it solves the problem. So there are other solutions that, for example, when you want to have digitization and energy harvesting, the other two blocks that I showed you. So you can again think of how to do that. So therefore now here we getting analog to digital conversion, which is for biopotential, but range of the frequencies in such a way that it can be used for many applications, because it's relatively a wide range of frequency, which is compatible with many sensors. And advantage is that it's completely passive solution. It's a continuous time delta sigma ADC, completely passive solution. And therefore the voltage range is very small. Required supply is very low. And we have a very nice design flow for that. And quantizer is just a simple 1-bit quantizer. And whatever summation we need, we actually have moved it to comparator to save power further. And this is very much compatible with the cases that you don't have any battery and then you want to harvest energy, which goes to many applications. So this is working, though it is in 180 nanometer SCL technology. This is very important. This is actually an SCL technology. It works at 1 volt and it covers signals up to 10 kilohertz. Therefore, it has a lot of applications. And the whole power consumption is around 600 nanowatt. And it is all because it is operated based on mostly passive components, as you can see. The delta sigma loop, you can see, is all mainly based on the passive components. Even for the DAC, we have simply used simple inverters. And here you can see combination of one energy harvesting chip that we have. Because of shortage of time, I'm not able to talk about that chip. But this chip eventually has 2 antennas at the input, in fact, connected to 2 antennas. One is used for measuring the level of the energy available in the ambient, and one is actually for getting the energy and converting it to the required DC values. So eventually we have a capacitor here, which is initially charged to 800 millivolt, but then we don't need to charge it again. This capacitor continuously gets charged with the input power level, and the design is in such a way that energy levels are really low at the input. It is nanowatt to microwatt. It's not really like hundreds of milliwatt. It's very low energy. And then we use this chip to empower the continuous time delta sigma chip, and then we put them together. And you can see very nice compatibility of the performance with respect to, this is FFT, which is very standard way of showing the noise shaping for the delta sigma ADCs. And also here we show one more thing is about, if we use a DC source, 1 volt, strictly DC source, we get SNDR of 55 dB. If we use energy harvesting chip, we get 54 dB. That's because the supply is not as regulated and clean as strictly DC source. But I think, losing 1 dB but getting a completely power autonomous chip is really fantastic. So the research scholars were very excited when they were able to eventually use a kind of batteryless arrangement. There is no battery here. There is no DC source over here, and operate the chip. So another solution also as a continuation of the same was done to reduce the supply further, and then we could reduce it to 300 millivolt. And we made another sensor, another chip, which this time it was made in UMC 180 nanometer, but with similar characteristics. Power consumption was still around 200 nanowatt, and SNDR was almost at the same level. But one interesting point here is the supply is now 300 milliwatt. Why? Because for energy harvesting systems, it's very difficult to get a very high DC level. So that's why bringing the DC low gives us the opportunity to reduce the required energy at the input. And again, this is the ASIC, and then this is the actual arrangement on the PCB. So this is again new, this is again indigenous in the sense that with respect to design, it can be migrated to a SEAL technology. So this is another example. And again, if you look at this, both of them, UMC as well as SEAL technology designs, they compete with the corresponding existing design with respect to the figure of merit, which is defined with respect to energy, which is eventually power dissipation divided by the bandwidth and 2 to the power enough, which is one of the figure of merits, which is used for comparison of the 3 things: bandwidth, power consumption, and resolution in ADCs. So the conclusion is that here we can have really a very nice low voltage design as low as 300 millivolt supply, useful for batteryless application, sub-microwatt power consumption, resolution is good enough for many applications, 9-bit. And of course, design is very compact. We don't need really too much because as you see, the circuit is very small and therefore RIO-wise also is very small. Therefore, it allows to have cheap IPs. And finally, another dimension is you may not really need always to measure everything. Sometimes you can estimate. In many sensing applications, you can estimate even when you need to have high accuracy. Specifically, I want to emphasize on high accuracy because usually estimation is considered for the case then we have low accuracy, right? But here is not the case. And I give you a kind of application which is gravimetric MEMS-based ultra-fine particulate measurement system. Ultra-fine means that particles in the air of which the dimension or size can reach as low as 100 nanometer and less. So current existing techniques like laser-based techniques are not very much useful for this technique because size is very low. So therefore this gravimetric MEMS space is another option. So here now we have eventually a MEMS element which is sensitive to the mass of the nanoparticles. And we want to use this technique to eventually go with a very high resolution. So it's very interesting to know that if we want to rely on gravimetric techniques and mass of particles of which the diameter can be as low as 100 nanometer, mass is not very high. And then even if over time we look at change in the mass, change in the, characteristics of the MEMS will not be very high. Now, what are we looking at this characteristics? Actually, we are looking at the resonance frequency. So therefore, nanoparticles will be deposited on the MEMS, and then we have an oscillator, and then we will have a very high resolution frequency to digital converter. So now here is the technique actually we used was not to measure accurately, but to estimate accurately. This is very interesting. And then we showed that it is possible to actually reach to a very, very kind of highly accurate measurement system, which is again indigenous system. And this system is eventually showed over here. On the left side, you see, of course, the MEMS or crystal. We have used even quartz crystal for the reference, in addition to MEMS. For the oscillator part.
Hello,
Yes.
Mariam ma'am.
Yes.
In the interest of time, if we can just speed up a little bit.
Sure. This is in fact the last part of my presentation.
Thank you, ma'am.
Yeah, sure. Thank you for reminding me. So this system, as you can see at the middle, it is again the same system and has relatively same components I told you. The only thing is that it has instead of signal conditioning, we have a kind of buffer and signal to differential conversion using COTS elements. So eventually this is not an ASIC, this is COTS. And then we have a wireless connectivity also to a laptop through Bluetooth to be able to get the samples. So this system we call ProFMS, Programmable Frequency Measurement System. And then it's very interesting to know that this system is again something that you will be able to make, and anybody will be able to make, but of course we need to put minds and then think and then see what we can do. But again, to give you kind of confidence and the kind of showing the glimpse of opportunity, I just showed the estimation techniques that we have used. There are various estimation techniques for frequency. We have used several of them, and then we have been able to show compatibility and competition eventually. Although I don't like the word competition, nothing is actually in competition. It's just a comparison. In comparison to Agilent frequency meter. So you see the numbers on the left side from frequency estimation. And then this is eventually delta F by F in ppm, which is pretty low, really pretty low. And this is one of the algorithms, Kandan algorithm. All these estimation techniques also are given in the appendix of the paper we have published. All these papers I have included in this talk are published this year only. So that's why they are recently reported works. We have even gone to another level where we have shown that even if we use compressive sensing and then we have less number of sensing for the faster measurement, we are able to still beat Agilent counter. And this is very much achievement. So therefore you can just actually make this system. This system can be made and this system can be used for such a high resolution frequency measurement. So this is actual setup for depositing the particles. This has been done with the help from our collaborator from Cambridge University, but you can see this ProFMS, our system over there, which has been used for the actual measurements. And we have also one system, which is CPC data logger for the comparison purpose. And this is eventually the photo of the MEMS device as nanoparticles are deposited on the sensor. And these are the measurement results over time, and then how it can really be compatible with the Agilent counter, because we use it continuously for the comparison purpose. So summary is that yes, high resolution can be achieved with a locally designed and developed frequency measurement system, which relies on the algorithms for frequency estimation. And it's very interesting to know that in the presence of jitter, we estimate the frequency with a very high accuracy. And therefore, we have been able to achieve the sensitivity of 16 picogram per minute as the system moves. Because this deposition happens on the over time. And Finally, I just give the overview of these 5 novel indigenous designs and prototypes that I talked about them with you. It started with a simple, easy manufacturable capacitive, leaky capacitive sensors up to a MEMS-based particulate sensor system. The different levels of accuracies required in each one of these applications. But just to show you how we can, in fact, move and navigate around these applications and make specific modular designs which can be reused. We have actually reused some of the ADCs that we have designed with respect to them. We have reused the signal conditioning circuit we have designed for other applications that we had. And we have enough flexibility to change them easily. When you get something ready-made from like a complete solution from market and from commercial, as a commercial product, you don't have flexibility to change them much. They don't have, in fact, too much flexibility. So this gives a lot of flexibility, and also, the design knowledge and expertise is developed. This is very important to look into. And then, of course, these modular solutions can continue to move towards various types of sensors. We need to look at them. We need to make them more integratable with self-powered systems, and we need also to look into more modular designs for background calibration. And finally, for the specific project at the end, we would like to have this kind of systems which can be installed in indoor and outdoor environments. So these projects have been financially supported by various government agencies through different programs, and also labs at IIT Bombay, that I acknowledge. Collaborators are listed here from various universities, specifically with respect to some of the sensors that we needed, with respect to strain sensors, MEMS sensors. They have helped us to get some of them. So this work actually is the work of 3 PhD scholars, Shahid, Laxmisha, and Meraj, 3 of them. All of them have submitted their thesis, and they are graduating this year. And this was a very nice journey with them. And of course, other teams, Adarsh MTech student who developed, in fact, Pro-FMS system, Ajay who worked on the frequency estimation, and Surya who helped Miraj in making the complete ASIC with 2 frequency modulation. Thank you.
Thank you, ma'am. Thank you for this very good talk. So, in the interest of time, we can have just maybe 1 or maximum 2 questions. So, if so, the session is open for question now. So, if anybody has a question, just feel free to ask. So maybe, madam, actually, I saw this fully passive the filters you have made. So looked quite good. If I mean, you have done it with SCL technology,
Yes.
which is kind of available in India itself. So
Yes.
do they have these active devices as well, or only the passives are available? And actually the question is, later you made it using UMC technology also. So
Yes.
how did you find the performance wise? How much is the kind of difference from HCL?
Okay. Yeah, thanks for your question. No, SCL, in fact, offers the active elements as well, because for the comparator part, as shown here, we needed to have transistors. So they provided us the transistors. And one thing I should mention about the model files. So in fact, we found model files which are given by SCL very much compatible with the measurement results that we got. In fact, we didn't get too much surprise after measuring, after measurement with respect to simulation results. So their models also are relatively reliable. The only point is it takes some time. In fact, one of the reasons we moved to UMC after that. So advantage here was we could get it for free, but point only was it takes some time. So therefore turnaround time is more compared to UMC, and that was the reason we also moved to UMC for the next design. But it was not the reason like we didn't get, we were ready to send the next one also to SCL, but because of saving time we moved to UMC. Now if you look at the comparison, I would say that less or more they are similar. A little difference we observed, only a little difference between the simulation and measurement was with respect to the noise models. So for the SCL, we observed a slight difference, while for the UMC, post silicon and pre-silicon post-layout simulations were similar, were closer. So it's only that difference, but that difference even in SCL is not in such a way that you will get completely strange results, because, for example, the SNDR we got around 55 dB. It was reasonably predicted by the simulation as well.
Okay, ma'am. So let me thank the speaker, Professor Mariam, from on behalf of the ICEE conference. Thank you, madam. Thank you for this wonderful talk.
Thank you for inviting me.
Thank you, ma'am. It's very good to have you, ma'am, here.
Yeah.
So, thank you.
Me too,
Thank you.
to be with all of you. So I'm sharing.
Yes, ma'am. So now let's proceed for our next talk. So the next talk will be given by Professor Mayank Srivastav. He is a professor in ISC Bangalore. I know him. I mean, right from the starting of my PhD, I worked under him for like a very long time. I really enjoyed working with Professor Mayank. So Professor Mayank received his PhD degree from IIT Bombay, and for his PhD work, he received Excellence in Research Award for his PhD thesis and Industrial Impact Award from IIT Bombay in 2010. He's among the first recipient of Indian section of American TR35 award, which is very, very prestigious awards. And he's the first Indian to receive IEEE EDS Early Career Research Award. Besides, he's an IEEE senior member and has received several other national awards and honors of high, like INAE, NASI, INSA, and INAE. Frankly speaking, if I talk about the awards he has won, I will need, I think, 30 minutes of session to speak about the awards. But just in a short, actually, his current research interest deals with the experimentation, design, and modeling of beyond CMOS devices using graphene and TMDCs, wide bandgap materials, ESDs, and in advanced and beyond CMOS nodes. And he worked for Infineon Technologies, East Fishkill, New York, USA, and IBM Microelectronics, Burlington, UVT, USA, and Intel Mobile Communication, New York, USA. He joined ISC as a faculty member in 2013, where he's currently working as associate professor. Associate professor. Professor Mayank has over 150 peer-reviewed international publications and 50 patents. So let me invite Professor Mayank. So Professor Mayank.
Yes, I hope I'm audible.
Please, yes, you are audible. Please proceed with your talk.
Thank you, Professor Gupta. Thanks to the organizers for inviting me for this session. It's my pleasure to give a talk at ICEE and talk about the work we have done. Since the invitation was from a modeling session, I thought, how do we restructure the gallium nitride work we have done and make it useful for the modeling community within the country as well as rest of the world. And that's why you see the title of the talk, which sounds as how we use the computational modeling and enabled the help of or enabled computational modeling based design approach. So enabled this for GaN-based power transistor and diode technologies. I will not cover very detailed physical insights here because I am going to summarize 30 plus papers that we have published, primarily focusing on development of the power transistor and diode technology with LGAN-GaN EP stacks. The focus is more on giving an idea of how computational modeling can be used. So you can think of this as a case study and something which hopefully will convince the modeling community to rely on computational modeling based approaches for GaN-based technologies. So with this is the outline of my talk. I'll quickly run you through why gallium nitride and what are the computational modeling challenges in gallium nitride technology. I'll try to convince you that this is not straightforward as silicon technologies. Then I'll cover what we have done or achieved as far as the GaN HEMT technology is concerned. In terms of developing physical insights for carbon doping, breakdown, surface passivation, and how it helped us in designing several aspects of the HEMT technology. Or let's say the physical insights or the design guidelines for field plate, which is a very important technology module for gallium nitride HEMTs. We'll show you how you can design novel field plates and improve the performance as well as reliability. I'll show you some of the details about a novel gates oxide that we developed. And that kind of enabled all of that work enabled us to demonstrate a technology which is 600 volt 4 amp enhancement mode qualified. And this is something which is ready to be scaled up, can be taken up to higher TRL levels and commercialized. Similar effort we put at the gallium nitride diode front. You know that in any power electronic system, you need a switch, which is a transistor, and a diode. So we worked on both. So for making gallium nitride diodes, we tried understanding, various aspects of gallium nitride based diodes in terms of reverse leakage, reverse breakdown, high current behavior, thermal aspects, thermal failure, field plate operation, and design guideline. And this enabled us in demonstrating 500 volt 15 amp kind of gallium nitride diodes. I'll also show you that how TCAD helped us in understanding some of the experimental reliability aspects which we could not understand from experiments, but we could understand from TCAD, and then eventually I'll summarize this talk. Let's start. So gallium nitride, as you know, that gallium nitride is a wide bandgap semiconductor. Compared to silicon, the bandgap is more than 3 times, and it's little higher than silicon carbide. And that's the reason why it has much higher, more than 10 times higher critical electric field than silicon. Not only the band gap, but unlike silicon carbide, it also offers higher mobility than silicon, and higher velocity saturation than silicon, while having comparable thermal conductivity. So these are the reasons you can think of improved breakdown voltage, shorter drift length. So a shorter drift length for a given breakdown voltage means a faster device, right? And of course a higher current density, and you have thermal performance comparable to silicon. What does this mean is that a GaN on silicon device can offer you a compact, efficient, and economic power electronic systems, and that's why there's a lot of push for gallium nitride based technology. This chart will tell you the same thing from on resistance versus breakdown voltage trade-off point of view, that for a given on resistance, you can achieve much higher breakdown voltage with gallium nitride based technology. And therefore, if you design for the same breakdown voltage, you can achieve much lower on resistance, which means much higher switching frequency. And that's the reason what you see in this chart, that in the early days, improvements in terms of switching performance and the silicon technology helped system designers to scale the system size and the cost. But of course, beyond a point, silicon technology also saturated in terms of the best performance it can offer, and therefore people started switching to gallium nitride because that can offer switching frequencies which are comparably higher than, relatively higher than what silicon can offer, and therefore you can further scale the system. And these are the reasons why gallium nitride is projected to replace 100 volt to 1200 volt kind of silicon or silicon carbide devices, in next 3 to 5 years. Now, what makes gallium nitride EP stack very unique? It has two important features, which are called spontaneous polarization and piezoelectric polarizations. These two are different, but fundamentally, what they do, if you stack two different materials or materials having different polarizations, you are going to introduce an electron gas at the interface. Now, this electron gas here is called two-dimensional electron gas. And because of the quantum mechanical features of this electron gas, you also get very high mobility and very high carrier density confined to a very short, very narrow region. Now, this is very unique to this kind of material system. When you stack, two different polar materials like AlGaN and gallium nitride on top of each other, you get very high mobility to 2D electron gas density with sheet carrier concentrations, as high as 10 to the power 13, which helps you getting very low on resistance behavior. It has wide band gap, which means we also get very high breakdown voltage, lower leakage, even at very high temperatures. So once you have IP stack, so what you see here is this is the AlGaN region, this is the GaN region, and then you have a lot of other regions which will help you doing the growth properly. And at this interface, which is the AlGaN and the GaN interface, you get a 2D electron gas, right? You have a silicon nitride, or you can have a gallium nitride capping on top of it. I will talk about that later. So now once you have the 2D electron gas, a sheet which is full of electrons, all you need is put two contacts side by side. That will make you a resistor or a resistive contact from source to drain. But you also need a gate to control the flow of the current. So you can put a gate on top of that. And now you can switch off the channel or switch on the channel. Now, what you notice is that if the gate is not there, the transistor is normally on, right? Or if the gate is not biased, the transistor is normally on. And that's very different than a conventional silicon kind of transistors or silicon kind of power transistors that we are used to of, or we are known of. So, and that's the reason why this kind of transistor is called normally on device. So this is another fundamental challenge with this technology. If you want to make a normally off device, which is called the enhancement mode device, which is what is typically desired for power electronic applications. A normally on device is good to go for RF applications, but if you want to use it as a switch for power electronic applications, or a RF switch in some other applications, you need to make it an E mode or a normally off device, right? So let's see what are the computational modeling challenges. So unlike silicon, this material system has very unique properties. I already talked about polarization, for example, right? And this heavily depends on the material properties. So you have to model some of the material behavior in an empirical or semi-empirical or semi-classical fashion to account for the polarization aspects at different interfaces. This material system is grown with CVD kind of methods or epitaxial methods. So since this is not single crystal material, therefore you have traps or defects present in the system, and you have to accurately model these traps or defects present in the system across all the interfaces in all the regions and so on. The gate leakage affects the performance and reliability significantly in a much more drastic way than it can happen in a conventional silicon MOSFET, and therefore you have to precisely model the gate leakage characteristic, gate leakage behavior under various conditions. Then you have thermal effects, you have hot carrier effects, and they do affect the performance, reliability, and many other aspects. Therefore, you have to model for the thermal effects and hot carrier effects as well. Then you have negative differential resistance. If you are designing a device for, let's say, RF applications, you need to account for NDR effects as well. So like what you see here, you have these NDR effects. The breakdown physics is very different than what you see in silicon MOSFETs. Therefore, you have to precisely model the breakdown mechanism, which involves a lot of dynamics from the traps. Then traps are also responsible for behaviors like dynamic R-on and current collapse. And therefore, you need to understand, the physics behind dynamic R-on, current collapse, and so on. And thereby, you have to model that. And contacts are also very different. So they are not usually ohmic contacts. They are often Schottky contacts with very small Schottky barrier height. And different kind of tunneling rates for electrons and holes. So you have to model the contacts accurately. I'll tell you more things about computational modeling as we come across in next of the slides. So this slide summarizes, what we do, how these various aspects affect which parameter or which behavior of the device, what kind of parameters we have to worry about, and what all kind of extractions, experimental extractions you have to do the calibration. And the plots that you see here, it shows that how nicely we have calibrated various aspects. So what you see, we could calibrate the IV behavior, including the NDR effect. We calibrated the leakage trends as well as the breakdown trends. We calibrated various other leakage mechanisms like the parasitic leakage from gate to source, source current and the gate leakage. And we also calibrated and modeled the dynamic R-on behavior in simulation. So what you see here is this is the dynamic R-on, which is the change in resistance after a certain stress, which is there on the x-axis. And we are able to capture this behavior in our simulations as well. And I'll show you some more aspects in the coming slides. Okay, so let's get into the gallium nitride HEMT, what we did. So we invested a lot of effort in understanding the physics behind carbon doping. Those insights can be read from our papers, but what we did with those insights and the framework that we developed, which can accurately model the carbon doping physics, we use that to come up with novel EP stack design. And for instance, in this case, what we propose that so fundamentally you need an appropriate acceptor trap and a donor trap ratio to be maintained for achieving very high breakdown voltages. The carbon doping will introduce both acceptor and the donor traps. And depending on the temperatures and other things and the conditions in which you grow, the acceptor trap concentration, the donor trap concentration will vary. So what we found is that when you grow, they both vary simultaneously. Therefore, you don't have a control between the acceptor trap, donor trap concentration, their ratios, and so on. So what we tried introducing, along with carbon doping, we also introduced silicon doping, which can introduce donor traps. And what we found is that by doing a co-doping of carbon and silicon, and and further optimization of the stack in terms of where you want silicon doping and where you don't want silicon doping, you can get a right optimum which can give you very high breakdown voltages compared to the case with just carbon doping. We also published another paper which came out recently in 2 parts, where we demonstrated that there's a dependence of breakdown voltage on surface traps, and there's also a correlation between surface trap and buffer trap, which defines the breakdown voltage. Now, having understood the surface trap and donor trap, surface trap and the buffer traps, the surface traps are dominated by the passivation that you put in. The buffer traps are dominated by the way you dope carbon in the GAN buffer. So we came up with this scheme which shows that you need to do a right optimum of the buffer doping and the surface passivation, which means that you have to do a co-design of buffer as well as surface if you want to get the maximum breakdown voltage. The other aspect of the gallium nitride HEMT technology I had shown earlier is a field plate. Field plate is a very important technology module. However, the literature as far as the field plate is concerned is quite scattered, and there is no consistency in terms of the physics behind field plate as well as which field plate methodology should be used. For instance, some people would use source connected field plate, some people would use gate connected field plate, some would use drain connected field plate. Sometimes they get achievement performance, breakdown voltage improvement with field plate. Sometimes they don't get it, and there's no clarity why sometimes you get improvement, sometimes you don't get any improvement, right? Then also, there's no clarity on, when you do the field plate design from the conventional silicon power MOSFETs, we know that the field plates are designed to basically engineer the field and engineer the charge distribution. Now, if you have serious charge distribution present inside your GAN system, which could be because of the polarization charge, buffer traps, surface traps. You have a lot more sources of charges present in your system. There must be some dependency on these charges and their distribution as far as the field plate design is concerned. And this is also something which nobody knew before our work. So the question was, can we understand how field plates affect or behave under the presence of various, aspects of the growth, and using that, can we come up with a unified design guideline for field plate designs in HELT? So, for instance, we investigated various things experimentally as well as using computations, and what we found that the passivation has a lot of dependence on the field plate design or the breakdown voltage, and that is because of the surface donor traps contributed by the passivation layer. And if you don't do the passivation right, which means if you don't optimize the stoichiometry of the passivation layer, which will affect the surface donor traps, you won't get the right maxima for the breakdown voltage when you put the passivation in place. So this is for the iron doping, this is for the carbon doping. The trends are also different because, in this case, what you see, in the case of carbon doping, the buffer has both acceptor and the donor traps. In case of iron doping, you have only acceptor traps, which means that the change in the breakdown voltage or the optimum of the breakdown voltage is not only dependent on the surface passivation, but also dependent on the way you design the buffer. So there is, a co-doping involved. Whereas the moment you do a two-terminal breakdown voltage measurement, there is no dependence on the surface trap, which means there's a lot of dependence on the surface trap or the passivation only when you have a gate on top of it. If you don't have a gate, if you just do a two-terminal breakdown, everything is purely dependent on the buffer doping concentration or the nature of the buffer. Moreover, when you introduce a field plate, the kind of performance improvement that you get because of field plate is also strongly dependent on the kind of buffer dopings you have and the kind of surface dopings you have. So, which means the field plate design, it's a co-design with the buffer as well as the surface passivation is something that we found, and is something that really helped us in designing efficient field plate design methodology. So as part of this work, we also found that the reason, in some cases you have a certain field plate working, in some cases you have a certain other field plate working, because the field profile and the location of the field also heavily depends on the kind of trap profiles you have in the surface and the buffer and the relative concentrations, as well as the relative concentration of the sheet, the 2D electron gas. Now, having understood the physics behind, what makes the field plate work and what makes them not work, and why something will break, and where the field will be located under different scenarios, we came up with this algorithm which helps us designing, field plate methodology when you want a gate field plate, when you want a gate and drain field plate, and when you want just a drain field plate. Having understood that, we deployed the methodology into designing the field plate. And what you see is that, once you have the field plate, the roll-off goes down, and you can significantly improve the breakdown voltage and get to the two-terminal breakdown voltage numbers with the optimum field plate design. But if you don't do the optimum design, then your numbers would be very similar to the case without field plate. And this explains why in some cases people don't get any performance or breakdown voltage improvement with the introduction of the field plate, where in some cases you get it. Okay, we also use this insight to come up with new kind of field plate designs. So what you see here is, in certain scenarios where the field would be peaking at both gate and the drain, what we thought, can we push the field peak far below in the GAN buffer with the introduction of these unique field plate designs. And having done that, we could improve the breakdown voltage without compromising with the on-state performance, which means when you scale the device for the same breakdown voltage, you significantly gain in terms of the figure of merit parameter for the new field plate method that we deployed. We also investigated, so this is the RF performance. What you see is a lot more linear compared to the other devices. And we also investigated the power amplifier performance using load pull simulations by doing the S parameter modeling of the devices. and we demonstrated that even at the power amplifier level, the proposed field plate design, offers much better performance than the conventional field plate. So this is all what you can do with computations, and then you can deploy, you can experimentally validate the technology, which I'll show you in some of the slides. The other problem that we worked on, and where the TCAD helped a lot, was designing of gate stacks which can emulate or which can give you a normally off or enhancement mode device. So as you know that for achieving enhancement mode devices, there are two different methods. One is that you deploy a p-type gallium nitride layer in the gate, but that requires a separate growth. Or the other method is, you do a full recess and make it normally off, but the moment you do full recess, you lose significantly on the performance. So our idea was, and the p-GaN gate has its own reliability issues. So our idea was, can we think of a gate oxide, which is p-type, which behaves like the p-GaN gate, but has all the gate oxide advantages. So we were investigating various things, and then there was a Eureka moment where we found that by doping tioxide with aluminum can make it p-type. And then we tried understanding various things with TCAD, that what kind of right thickness concentration that you need to make it normally off. In terms of band diagram, normally off means the Fermi level should shift away or below from the conduction band minima in the 2D electron gas. And by the right optimum, we were able to do that. We did a lot of simulations to understand, how much thickness, concentration, energy level of the traps are required to shift all those things. Then we did a lot of process optimizations to achieve those numbers. And then what you see here is that experimental demonstration of a threshold voltage shift from a normally on operation to close to normally off operation. However, what we found was that this itself was not sufficient to get normally off. Though we had a 3.8 volt threshold voltage shift, we wanted 1 extra volt of threshold voltage shift. So for that, again, we did some simulations. We found that if we thin down the barrier just in the gate region a little bit, we can further shift the threshold voltage. That's what you see here from simulations. And then we investigated that further in experiments. So we did again some optimizations, and then we were able to demonstrate these normally off E-mode devices, with 610 volt kind of breakdown voltages, very small gate leakages. And of course, all the designs related to passivation, field plate were deployed from the previous understanding here. Right. So what you also see is a nice control on the threshold voltage shift here. We could achieve these red lines. We could achieve the shift in the threshold voltage to the positive side, so making it normally off devices. You also see with this new gate oxide, the subthreshold slope was significantly reduced with a positive threshold voltage. And not only that, we also improved the safe operating area reliability using the understandings that we developed. So what you see here is, the threshold voltage tunability for various process runs that we did, and depending on, how you activate those traps inside the aluminum dioxide, the ternary oxide, you get different kind of threshold voltage shifts. So you see record high performance numbers in terms of on resistance or on currents, and a nice IV characteristic for the transistor that we demonstrated. We did not stop there. We also investigated a lot of reliability things. So we translated the technology to make high current devices. And what you see here is, 600 volt, 4 amp kind of technology, which is available, and it can be scaled up for integration at the systems level. Now I will switch gears and I'll move to the gallium nitride diodes, and I'll show you what we have done and how we could achieve the technology, which is 500 volt and 15 amp technology. So the way gallium nitride diodes work, conventionally, people thought that they will put an anode on top of silicon, on top of LGAN, and you basically get a Schottky barrier between metal and LGAN. But this Schottky barrier was too high because LGAN is a very wide bandgap semiconductor. So this kind of Schottky barrier you introduce would be very high, and that kind of diode used to give cut-in voltage of 2 volts to 2 to 3 volt, and nobody wants that kind of diode. So what we thought, can we bring the anode down and make the Schottky contact directly with the 2D electron gas? and that actually worked. So then we investigated various aspects in terms of the leakage, breakdown, tunneling, thermal, and so on. And we came up with this with design guideline and used that for developing the technology that I'll show you. So we could accurately model the interface states at the Schottky interface. So that we can model the leakage behavior and the breakdown trends. What you see here is a nice calibration between the experiments that we did with the diodes that we realized and the simulations. So there are various things that you need to optimize or need to understand as far as the technology is concerned. You need to work on the anode recess, which will affect the breakdown voltage, the cut-in voltage of current. You have to work on the Schottky interface, which affects the breakdown voltage and the off current. You have to work on the buffer type. You have to work on the field plate, which will affect the breakdown voltage, reverse and forward recovery, which we experimentally measured and matched with computations. Electrothermal behavior as well. So we could find the origin of the reverse leakage. A lot of experiments that we did, and we published a separate paper, experimental paper where as a function of various treatments, we have found that how the reverse leakage varies, and for various treatments we could measure the traps, and then we modeled it back into the system that how these traps affect the breakdown and the leakage behavior. Right, so we were able to understand the physics in terms of what affects the leakage and the breakdown behavior, and the role of different kind of traps, acceptor and donor traps at the interface in terms of affecting the cut-in voltage as well as the reverse leakage. With this understanding, we came up with a scheme to passivate these excess traps, suppress the leakage, and improve the breakdown voltage. And we demonstrated that at experimental level as well. For instance, we introduced these additional passivation traps with some of the plasma methods. And what you see is as you increase the trap concentration, the reverse leakage falls down significantly and the breakdown voltage improves, demonstrated experimentally. Then we also worked on recess depth optimization. And what?
So, Professor Mayank, if we can little speed up the
Yes, I
presentation.
will conclude in 5 minutes.
Thank you.
So what you see is that experimentally how the recess depth can improve the breakdown voltage, and depending on the kind of buffer you use, whether iron doped or carbon doped, you can also play with the breakdown voltage. So one has to account for the buffer doping along with the rest of the optimizations that you do. I'll skip some of the other details that we investigated. For instance, we also investigated the role of the field plates in these diodes and how you can design the field plate to experimentally to improve the breakdown voltage that we see here. So you need a right optimum field plate length to improve the breakdown voltage. And then what we also found that you can also design a thermal system or a heat sink on top of the device using the field plate and improve the performance further. And that's what you see here, that when we have the heat sink on the device, which is thickening of the field plate, the thermal performance improved significantly, and therefore the forward current improved significantly. This is also the experimental demonstration of this 500 volt and 15 amp diode that we demonstrated. Quickly, we worked heavily on the reliability behavior of these devices as well. So for instance, in one of the paper where we demonstrated improvement in the reliability or the safe operating reliability behavior as a function of certain design parameters, for example, recess depth, we were able to understand the physics by doing TCAD by showing that the field pick shifts from the critical location, which is gate, to the non-critical location, which is drain, and that's how the reliability behavior or the safe operating area reliability improves as a function of certain traps and the recess depth. In another work, we discussed presence of the parasitic conduction path, and we validated and presence of the hotspots at critical region, and we validated that with TCAD computations. And in another work, which is on reliability of these Schottky diodes, we worked on the reliability of high current behavior or reliability under high current conditions of these diodes, and we were able to understand why something fails. So finally, let me summarize what we learned or what we have seen. So computational modeling of gallium nitride HEMT and diodes is challenging. But a well-calibrated framework can accurately predict the technology trends and underlying physics. We could model every aspect, which allowed us the following. So for instance, we probed physics of carbon doping, and that allowed us to design better EP stacks or make proposals for better EP stacks. We invested efforts in understanding the interplay between surface and the buffer, and that helped us in designing improved surface and passivation methodology. We could accurately predict the characteristics under various conditions. So that helped us in designing improved power and RF devices. We understood the physics behind field plates, so that helped us in doing field plate design guideline as a function of AP stack and passivation, and also come up with optimum field plate design. And we also helped in, we also understood the mechanism responsible for E-mode operation with the P-type oxide, and that helped us in demonstrating enhancement mode HEMTs. We also developed physical insights into breakdown physics, high current behavior, thermal trap-assisted failures, and that helped us in getting improved 3-terminal breakdown greater than 600 volt and improved safe operating area reliability. And at the diode front, we could understand the recessed diode operation. We developed design guidelines. We developed physical insights, reliability, and thermal behavior, and that enabled us demonstrating high current, high voltage diodes. So as a result of all the insights that we developed, the guidelines that we developed, the computational investigations we did, along with all the experiments that we did, we were able to demonstrate 600 volt 4 amp enhancement mode HEMT with record high performance, and say 500 volt 15 amp gallium nitride based Schottky diodes. I would suggest the audience to go through our publications to get more details about this. And with this, thank you very much. Thanks also to funding agencies which have supported the gallium nitride program at Icee. And with this, thanks a lot to the audience and the organizers. And I'm open to take any question.
Thank you, Professor Mayank, for the very good talk. So we can have any question if there is.
So may I ask a question?
Yes, ma'am. Yes, ma'am, please.
Yeah. So nice talk, Mayank. I have a question. So you said that you have calibrated the simulation with the experimental results that you have performed. So have you made the devices in Icee?
Oh yeah, all these devices are done in Icee. The technology that I had shown is the technology that we developed here in Icee in my group.
Okay, very good. Very good. So therefore, you are able even to apply the optimizations that you talk about, even and make the optimized devices, right?
Oh yes, yes. So TCAD is part of the whole methodology or the work framework. But I have presented it as it was a lot of TCAD work, but it's a lot of device design, process optimization work, and we do TCAD to understand, or get the directions in which we have to, proceed at the experimental front.
Right, of course. No, because see, this is a very systematic approach, and the way you had elaborated with your research scholars. So I think, it's very interesting to see that, for example, when you really develop the insights using TCAD, do you have that kind of flexibility also to incorporate into the actual fabrication?
Oh yeah, I mean, anything that we have done with TCAD that we have incorporated in experiments, and many times we have done the experiments first and then we have done the TCAD. For instance, the E-mode device that I demonstrated, it's not that we did something with TCAD and then we processed the devices. We were actually, the reason I called it a Eureka moment, because we were actually processing a lot. We were optimizing aluminum oxide dielectric, and suddenly what we saw in one of the lot, the threshold voltage was somewhat higher and the leakage was very low. We could not understand why we do get this behavior. We went back, we did some XPS, we found that there is a titanium contamination in the dielectric. Then we did some atomistic computations to figure out how the band structure of a titanium aluminum oxide look like, and what we found that if you have a titanium oxide with aluminum, that's a p-type semiconductor, which is actually used in when a titanium oxide is used in sensors literature as a semiconductor, and if you dope it with aluminum, it becomes a p-type semiconductor. And then we thought, okay, if it is a p-type semiconductor, can we optimize it further to make E-mode HEMTs, because the E-mode HEMTs has actually a p-type semiconductor, which is gallium nitride. It also has the same band gap. Titanium oxide would give you 3.2, 3.4 electron volt. Gallium nitride will also give you 3.2, 3.4 electron volt. So we thought, can we replace gallium nitride by aluminum titanium oxide? And that's where the TCAD got into picture. We tried understanding, what kind of designs you have to do, what kind of oxide thickness you have to achieve, what kind of p-type concentration you need to get a E-mode behavior. And that's where we investigated a lot with TCAD. We came back, we did again, at least 50 different process runs, and then we achieved that technology.
Okay, very interesting. So then actually started from titanium contamination, right?
Yeah. So in fact, most of the TCAD work that you see is more recent than experiments.
Okay.
A lot of TCAD is inspired by many things that we observed in experiments, and then we tried understanding things. If we are not able to understand from experiments, we tried understanding from computations, because computations can give you a lot more flexibility in terms of the kind of probing that you can do versus experiments.
But this is very interesting, because you have been able eventually to have a kind of compatibility between the two, and then this getting from contamination to the actual idea, that's even more interesting. Okay, right. Very nice. Thank you.
Thank you.
Thank you, Professor Mayank. I thank you for giving the talk here in ICEE. Thank you very much.
Thank you.
Now,
thank you very much.
So now our next talk, Professor Atmesh Srivastav from Northeastern University. So I do not see him in the hall. Morning, I had conversation and he was like ready to join that time, but because of I don't know the US timing or something, he's not approachable also now. So let's we can cancel the talk, or at least postpone the talk for a later in the day. And after that we have a talk from Professor Albert Chin from NCTU Taiwan. So this is actually the invited talk. Actually, it's not an oral presentation by the student. This is actually invited talk, and it will happen tomorrow at 11 o'clock. So mistakenly they submitted the paper along with oral presentation, so that's why the name came here. So this talk is an invited talk and will happen tomorrow at 11 o'clock. So we can join that time. Now we have our last talk. This is a student oral presentation by Miss Shraddha. She's from IIT Delhi, and the title of the talk is optimization of drain extended MOS devices for reliability in high switching applications. So I welcome Ms. Shraddha. Ms. Shraddha, are you there?
Yes, sir.
Yeah. So you can please share the slides, and you can.
Sure. So I'm trying to share the screen. Is it visible?
Not yet. Just wait a minute. Screen is not visible till now.
Oh, so I'm trying here.
Mm. You know, there is a button called share right in front. So you're using that? No, still your name is there, but no screen. Hello, Shraddha. Miss Shraddha, are you able to share? Hello, am I audible?
Yes, Ankur, you are audible.
Uh, okay, but uh, mm, mm, hello, Miss Shraddha. So, Miss Akansha, any volunteer actually has the
Yes, sir.
contact?
Yes, sir. Give me a minute. I'll just call him and check the status.
Yes. So I think we will wait for 2 more minutes. Otherwise, we can reschedule this talk for the later in today. We have another session from 2 to 5. That time we have free slots. We can reschedule this talk. So let's wait for 2 more minutes. Hello, any volunteer? Any update?
Sir, she's not reachable. I'm trying, still trying.
Okay, so maybe some technical issue or something. So I'm sorry for this kind of this technical problem happening. So so this was our last talk, and if available, it will be rescheduled to the next session, maybe later in the evening. So thank you guys. Thank you all for joining the session and for your valuable discussion. The session will close now for the lunch break, and it will resume in the same hall number 4 at 1:30. So please do join us, and that session will be chaired by Professor S.P. Tiwari from IIT Jodhpur. So, thank you all for joining us. So we can drop the call now. This conference. Thank you.
Uh, Hi, Dr. Ankur. Are we starting now? Can you hear me?
So am I audible?
Yes, Professor Tiwari, you are audible.
Okay. So I think we should. So let's see the schedule. Okay, I think so. Without any further delay, we start the proceedings of this session. So I'm Srinath Tiwari. And let me introduce the first speaker, who is Dr. Abhishek Srivastava, who is an assistant professor at Triple IT Hyderabad, and he works at Center for VLSI and Immune System Technologies. He has received, so Dr. Srivastava has received PhD in electrical engineering from IIT Bombay. And after that, he had worked as a postdoctoral fellow at Purdue University at Department of Electrical and Computer Engineering. And his primary research area has been RF and analog circuits and system sensor-based applications. Obviously, this will be very useful for current IoT needs where sensor interfacing are one of the crucial aspects. So let us welcome Dr. Srivastava. So if you are ready, you can share your slides and we can begin with your presentation. And the talk title is on achieving the fundamental limits of phase noise in wave oscillator with on-chip MEMS resonators. Very interesting talk. So let us hear from Professor Srivastava. Thank you.
Yeah. Thank you, Professor Tiwari, for the quick introduction. And also, I thank the organizers of ICEE 2020 for inviting me for this talk. So let me share my screen and can you see my screen?
Yeah, it's visible.
Okay.
I think you can, go ahead, please.
Yeah. Okay. Yeah. Thanks once again, Professor Tiwari, for the introduction. And today I'll be discussing my title of my talk is on achieving the fundamental limits of phase noise in millimeter wave oscillators with on-chip MEMS resonators. So let me begin with a quick motivation for this talk. So at present, there has been an increasing demands of high-speed wireless communication in recent past. Not only for fun activities like gaming or movie, but also for accomplishing critical tasks such as remote surgeries, um, some nuclear power plant control, or massive machine type communications, or self-driving cars. All these controlling things in real time with very low latency. So all these applications basically need very high speed, which in turn requires a lot of bandwidth for wireless communication, something like hundreds of megahertz to few gigahertz, as is specified in 5G standard, which is being developed as the things are progressing. So for all these critical tasks, we need very high bandwidth, which requires very high carrier frequency also. It's not possible to achieve say few gigahertz of bandwidth at very low carrier frequency. For example, if we consider present day say 900 megahertz ISM bands or 2.4 gigahertz wireless bands, they are not good enough to give these high bandwidths. So obviously we need high carrier frequencies, something like more than 10 gigahertz. So 5G specifies a sub 6 gigahertz band, where most of our Wi-Fi routers in our home and offices work, but still technology is trending towards higher and higher frequency, moving into millimeter wave spectrum, which is more than 10 gigahertz frequencies. And this is not too far. In fact, recently, Qualcomm's Snapdragon X55 platform and recently launched Apple's iPhone 12, they use 5G communication in this millimeter wave spectrum also. It's not that they are using only 6 gigahertz, but they are using millimeter wave spectrum around 28 to 30 gigahertz for real 5G applications, communications. So this millimeter wave is a reality now in 5G domain. So uh, let us quickly see what are the methods with which we can achieve these high bandwidths, like a few gigahertz of bandwidth. First, we saw that high carrier frequency is indeed important, and the other method, which is quite frequently used or looks very promising, is bandwidth aggregation by multi-channel integration. Like we can have massive array of transceivers where we can combine these signals to achieve higher bandwidth with different higher order modulation schemes and so on and so forth. So here question arises is that how to generate a millimeter wave carrier efficiently for a large array of transceivers where we can further utilize and combine these signals to achieve further higher bandwidths. So with this motivation and question in our mind, my objectives of the today's talk is to introduce you to CMOS MEMS hybrid oscillator, which is an important research area, and it's very demanding at present. We will see why, and for this I will introduce you to I'll take one specific example of a millimeter wave MEMS resonator and walk you through to the challenges that are there and how to overcome them with a specific example. And during that, I will also discuss how we can push the existing fundamental limits of phase noise and oscillator figure of merit while utilizing the methods proposed here. And finally, I will conclude my talk with the future in this area. So before I proceed, I would like to acknowledge Dr. Shreya Sen, Dr. Dana Weinstein, and Spark Lab at Icee department, Purdue University, United States, where most of this work was done. So let me discuss, what are the choices do we have for high frequency generation? High frequency, I mean to say the millimeter wave. What are the choices do we have? So as you can see on the left, we have, say, this big chip where we have multiple, transceivers. We call it as say channels, where we want to give clocks or where we want to generate high frequency carriers. So first choice is obvious, is that we can have a common RF source frequency synthesizer at the center and can distribute that clock or that source throughout the chip. But the problem with that scheme is that first of all, we will burn a lot of power in routing, and secondly, we will lose control over the phases of the clocks or the signals reaching at different transceivers across the chip. So what is the second tempting solution? Second thing we can think of, that we can use separate frequency synthesizer for each channel. Okay, that sounds good. So usually how we make those frequency synthesizer? Using a PLL, right? So we typically have a PLL which is logged with the reference frequency, and reference is usually generated using an off-chip crystal shown in the right figure, where I'm pointing right now. So, but with this scheme, having different PLL and crystals for each channel will make your chip very bulkier, and it will no longer be an fully on-chip solution. So, what is desirable actually? We want local frequency synthesizers. We want high oscillator density for the chip, but at the same time, we want it to be crystal-less for reduced bill of material and PLL-less for reduced area and power. So what is the alternative of this PLL and crystal combination? So recently, researchers have come up with various efforts and have shown very high quality factor on chip MEMS resonators. So, for example, recently Dana's group has shown a resonant FinFET in 40 nanometer global foundry process with the quality factor much greater than 1000, near 30 gigahertz. And this was, they have made one FinFET based resonator using Bragg reflectors and designed in such a way that the die area was just 10 micro by 10 micro, which is incredible. So if somehow we are able to utilize this resonator and make oscillator out of it, then it is a breakthrough. We can overcome the problems discussed, that bulkier, costlier, and good phase noise, low power, all those problems will be solved. So let us see in that direction what are the challenges that come through this resonator. So here on the left side, I'm showing a typical Butterworth Van Dyke model for a resonator, where we have a series RM-LM-CM branch, which is also called as motional branch, and we have the C0 capacitances, which are called static capacitances, which arises due to the geometry and size of the device. And if you see, this type of resonator has two resonance modes called series resonance and parallel resonance mode. So if at resonance, this is the impedance plot across the two terminals of the device AB, and at resonance it becomes purely resistive. So at resonance, if we can have a negative resistance in a positive feedback loop, then we can have sustained oscillations. So that sounds very good and simple, that okay, we can put a negative resistance across the resonator and can make the oscillator. And that is how the crystal oscillators or many resonators based oscillators are designed. So what is the challenge here with this MEMS resonator? To understand that, let me share this table with you, which shows different electrical parameters for different resonators from 45 megahertz to 30 gigahertz. So they all have very high quality factors. I would like to bring your attention to the last column, where you see the reactance of this static capacitance to the ratio to the motional branches resistance ratio. It becomes almost same at very high frequency, right? It makes sense also. At very high frequency, this HCO will be very small, 1 by j omega c. So omega is very large. The resistance seen in this path from A to ground will be very high. So this XCO becoming equal to or comparable to RM is a problem. And what problem does it cause? So let us see through this picture. First of all, this very large XCO, what will happen if you try to make this kind of oscillator? Whatever signal, AC signal is going at point A will see a low impedance path to AC ground and will flow through this path, right? So in that way, your drive requirement for designing this oscillator will be very huge, and you might not achieve the gain Barkh-Hessian criteria. It might be very difficult to meet. Secondly, if as we discussed, the resonator should act as a purely resistive element at resonance. That is, its phase of its impedance should be 0. So if we calculate the condition for its phase to be 0, the static capacitance required to be this value. So for the parameters shown in the previous page, the required C0 will be about 1.6 femtofarad. And for practical consideration, this 1.6 femtofarad is not feasible for having that high quality factor. So for this, you may refer to Dana's paper shown before. So having this C0 1.6 femtofarad and at the same time having quality factor of greater than 1000 is not possible. And this picture on the left side shows again the phase plot for the resonator, the parameter listed in the previous slide, and it never crosses. On the right side you see the phase values, it never crosses the 0 value. So basically you cannot make an oscillator with this simple technique. You have to make this phase 0 first, and then you can think of your circuit topology. So what are the possible solutions to make that phase 0, to utilize it at resonance? So we want to...
yeah, please proceed. There was, I think, a bit of interruption.
No problem. Thank you. So we can, compensate. We can make that to phase 0 by, either series compensation or a shunt compensation. So with proper choice of these components, L series and L shunt, you can make your phase 0, right? But the first topology where we want to, compensate with the series connection, the problem of signal losing to AC ground does not solve. Right. Whereas in the second case, we can completely resonate out this C0 with L shunt, and it solves both the problem of getting this 0 phase and the signal loss to AC ground. So this shunt inductor compensated MEMS resonator sounds a reasonable choice, for the compensation of static capacitor. But when we put an inductor, inductors are usually will have very small quality factor. So what will happen to this modified structure? Will the benefits of high quality factor of the MEMS resonator be still there, or how it will be affected? Let's try to see that. So to answer that question, let us break this modified resonator into two parts, a series RLC, the motional branch, and this parallel LC combination. So overall impedance of this structure will be parallel combination of series RLC and parallel LC, which is shown in this plot. So series LC and parallel LC, if you take parallel combination, you get this green curve of the combined structure. And as you can see, if these two resonances are fairly matched, the parallel LC and series LC, then the green curve is also showing a high Q response, right? Which makes sense. So, however, this modified resonator will have a different quality factor than the original MEMS resonator. Let us call that loaded quality factor. And if this plot shows the loaded quality factor as a function of quality factor of the MEMS resonator for different values of quality factor of shunt inductor used for compensation. So we have shown in our paper in detail. In interest of time, I'll not go into the derivations. You can find these conditions. We have derived these conditions where for a given value of MEMS resonator's quality factor, your loaded quality factor is not affected by the quality factor of the shunt inductor. So for example, in this specific case, if your quality factor of MEMS resonator is greater than 2000, then your loaded quality factor will be almost equal to that. So you can have the benefits of the high quality factor of MEMS resonator, provided this condition is matched. Having said that, there is one another, very interesting aspect of this modified structure. So as we discussed, there are two resonance modes due to L0 C0 and due to RMA, this motional series branch. If there is a mismatch, wide mismatch between these two resonances, we'll have a curve like this. And you can see that at peak is occurring at this resonance point. So your maximum loop gain will be occurred at this point, and your oscillations will be sustained at this frequency, which is due to L0 C0 combination. And also the quality factor will also be governed by the L0. So you will again lose the high quality factor benefit if the resonances are mismatched widely. Whereas when your two resonances are matched, you get very high quality factor. Though the flip side is that your impedance amplitude and hence your carrier power reduces, I square R. So there is a problem that your carrier power reduces, but at the same time, you gain your quality factor improvement, say from quality factor of 10 to quality factor of 2000. And since your phase noise is inversely proportional to your carrier power and quality factor square, so this reduction in carrier power, basically your enhancement in quality factor dominates and you get an overall improvement in your power factor. So this is the intuitive way of understanding how can we get phase noise improvement using this technique, provided our this resonance should be matched. Okay, so moving further, if we want to do the phase noise analysis for this paper, I'll again give you the important insights here. Detailed derivation you can see in our paper. So basically, for phase noise analysis, the main noise causing elements in the system are this motional branches loss Rm, the shunt inductors loss RLO, and the active circuits noise, flicker noise, thermal noise, and again because of the structure and different transistors. So here usually tail current contributes the maximum flicker noise, which is an up converted to phase noise. So based on this, we did some derivation and found the minimum. So here in phase noise expression on the top, you see this F factor. So this F factor is basically, it is the noise factor of oscillator, which is defined as the total oscillator phase noise normalized to phase noise due to MEMS resonator's loss, which is RM. So we did, with all noise components, flicker, thermal, you can substitute and derive these things. So important point here is that, as I mentioned in the previous slide, because of the improvement in loaded quality factor with the technique discussed like resonance matching and shunt inductor compensation, we can get an advantage in figure of merit of the oscillator as well as the minimum noise factor of the oscillator. So with quality factor say increasing from 20 to 2000 will give you huge benefit in your phase noise as well as in your figure of merit. So for example, till now the oscillators with which are around 15, 20, 30 gigahertz oscillator, reported oscillator state of the art, are built using different LC topologies, where the state of the art number for FOM has been around 200 dBc per hertz, and phase noise is around 120 minus 120 dBc per hertz at 1 megahertz offset. But because of this high Q of the modified resonator and with proper design choices, we can have shown that we can push these limits fundamentally to these numbers, which are way ahead as compared to the reported literature. So, in order to validate the proposed, technique and methods, we did design one oscillator in 14 nanometer global foundry process, and the post layout simulation results here were very promising, and we could get, better than 130 dBc per hertz phase noise at 1 megahertz offset for 30 gigahertz carrier, and it was pretty much uh, uh, good with respect to resonance matching also. So you have this L naught C tank, right? So you can vary the tank capacitance and play with the tuning of this tank in order to match with this resonator's frequency, series frequency. So if there is a mismatch, then this range of capacitance refers to about 100 megahertz of mismatch. So within 100 megahertz of mismatch, still our PN phase noise is less than minus 120 dBc per hertz. So based on the technique proposed, here we are showing the comparison. So so all works here are measured, and we are showing here simulated work. But purpose here is to highlight the technique and methodology by which we wanted to show that it is possible to utilize, and we presented the methods how you can make you use this high Q on chip MEMS resonator at 30 gigahertz or millimeter wave frequencies, and can build oscillators with figure of merits like more than 200 while consuming very small power, and at the same time it's completely on chip and area is very, very small. So yeah, so I would like to now summarize this work, and will say that it is possible to build PLL-less, crystal-less oscillators for reduced bill of materials with high Q on-chip MEMS resonators, provided we analyze, this static capacitance effects properly, design the resonance matching elements carefully, then it is possible to, build on-chip very high quality oscillators. And moving ahead, this high static capacitance has been, a great problem in the fraternity, and people are trying, interesting ways to overcome this issue. So recently, people are trying to make active modes of resonator, where you excite one side, say driving side, and sense from the other side, but they two are disjoint. They are not physically connected. Means there is some type of mechanical transduction is happening. So a simple circuit equivalent of this active mode could be like this, where you drive at one input and sense current at other output, so that you don't load your output. With current sensing you can avoid that loading of this resonator. So again, this is an interesting thing, and here your input voltage and output currents will have some special phase differences, and in order to develop a voltage control current source resonator based oscillator with certain phase angle between them, it is really an exciting direction and interesting work to do with. So yeah, so with this, I think I would like to conclude. Thank you. If there are any questions, I'll be happy to take them.
Thanks, Professor Srivastava. So due to kind of to stick to time lines given, probably we'll have
Sure.
one quick question from the audience.
Sure.
So if there is any question, you can just type in chat box and I can. Okay, so Dr. Srivastava, I just wanted to know this kind of design is kind of what I find is it requires a lot of analog components design. So how is to get this fabrication done and at least check your ideas whether they are. So what kind of designs do you do for these inductors and capacitor? Are they kind of same as you do for?
Yeah. So for this, we had access to 14 nanometer Global Foundry libraries, and we did one design, and it was fabricated, and it is under measurements right now. So we used, say for example, if you see this circuit.
Yeah.
So the transistors and capacitors, inductors. So inductors, we have used library inductor here because we needed in our design about 200 picohenry inductor, and which was not consuming much area. It is 14 nanometer, and the overall area of inductor was also small. And for various capacitances, we use MIM capacitors, and also for this capacitor bank, we designed MOS cap capacitor bank. And others are, usual references, and transistors are already there in the technology.
So I think thank you so much. Probably this chat thing, and we may not get that many questions. So
no problem.
We'll go to the next talk, and thank you again for
Sure. Thank you, Professor Tiwari. Yeah, thanks. Bye-bye.
Okay, so our next speaker is Professor Yogesh Chauhan. And Yogesh has been a very good friend of mine, and almost he's so friendly that many of you might have interacted with him. So it's my pleasure to introduce him in this session. So start with say the title of his talk is Negative Capacitance Transistors, Modeling, Simulation, and Processor Performance. And it's just a formality to introduce him, so everybody knows him well. But then I have to do this duty. So he's a professor at IIT Kanpur, and see, he was with this IBM Bangalore SRDC during 7 to 10, and then he was there at Tokyo Institute of Technology, then UC Berkeley. So all these exposure and experience he has worked at ST Microelectronics also, and he has been a developer of several industry standard models, including this ASM again HEMP model, DSM bulk model. So a lot of things he has been doing, and probably his work shows this. And I want to congratulate him also. Yesterday he was also announced as a fellow of IEEE. So proud moment for us. So he has been editor of IEEE Transaction and Electronic Devices. He is distinguished lecturer for IEEE EDS, member of IEEE EDS Compact Modeling Committee, and fellow of Indian National Young Academy of Sciences. So he is vice chairperson of IEEE UP section. So he has been a very active person, and probably the younger generation working in this modeling and simulation and other device areas look up to him. So I'll not take a lot of time to introduce him, but I welcome him to start his talk, and then we all will be kind of listening to him. Yeah, so you guys, please share your thoughts.
Thank you, Professor Tiwari. So let me share this. So if I am correct, I have 30 minutes total, or how much?
So you have total 30 minutes. So 25 minutes we'll have talk, and 5 minutes. And because there are not many question answer kind of thing, so you can take up to even 27, 28 minutes, and maybe 2-3 minutes.
Sure. So please stop me like 2 minutes before the time.
Yeah, sure.
So let me share this. Okay, good afternoon. I'm going to talk on negative capacitance transistors. And here I will be mainly talking about modeling simulation of these transistors. Just to introduce, this is my group at IIT Kanpur. I have a team of close to 40 students and research scholars. We are regularly publishing in journals and conferences, and we have state-of-the-art device characterization laboratory for silicon and gallium nitride devices. If you are interested in using, please feel free to contact me for using these characterization facilities at IIT Kanpur. So before I go into the device, let me tell you on what is a compact model. So many of you work in the device area and you know the TCAD simulation, where you can do a lot of in-depth analysis inside the device. When it comes to compact model, you are going to describe the capacitance and current characteristics using only terminal voltages. So you can describe the DC and AC behavior or dynamic behavior using just these quantities. So it is a much simpler compared to the TCAD, and correspondingly it takes much less time in simulation. So this is how we describe the compact modeling. Once you are having good devices in Foundry, you need to pass that information to circuit designer, and this is done in the form of compact model. And there are a lot of requirements of a good compact model, especially in terms of convergence, time, and accuracy requirements. And these are some of the industry standard models like ASM, HAM, BSIM models. So what are the challenges in compact modeling? You can see that we really work from starting from materials, talking about the different material properties, then understanding the physics of the device, electrostatics, transport. For example, nowadays you need to take care of the ballistic transport or quasi-ballistic transport. Then you need to also know mathematics and computer science in terms of how to solve the equations, how to implement those, and implement those efficiently. And at the end, all these must satisfy the final requirements of circuit designers, what type of circuit he is simulating and whether the HEC is getting the required performance from that circuit. So we work all the way from materials to the circuit level. So this is the outline of my talk on the negative capacitance devices and mainly on the transistors. So I start here with this sub-threshold swing, which we all read in textbook. So this is given by how much voltage is required at the gate terminal for 1 decade change in current. And we know this equation for the sub-threshold swing, which you know at room temperature is that you have 1 plus C semiconductor by C insulator into 60 millivolt per dp. So you can see that this sub-threshold swing, which is this region, you have minimum 60 millivolt per decade at room temperature. Now we know that this leakage current or off current is governed by this sub-threshold swing, provided you have fixed your threshold voltage. And if you want to reduce this off current, you have to make this steeper. That means you have to do something with this expression. So what is the definition of capacitance? This is coming from textbooks. You can describe this as inverse curvature of free energy density. That means 1 by del square G by del P square, or also in terms of the slope of polarization versus electric field. And based on this, we can call dielectrics or nonlinear dielectrics as two types: paraelectric, that means there is no polarization when you remove the electric field, and the ferroelectric materials or dielectrics which have two possible states of polarization when we remove the electric field. So coming back on the definition which we were having, these capacitances, we can make the slope or sub-threshold slope steeper by playing with these capacitances, provide one of this is negative. Now if one of this is negative, that means let's take insulator capacitance negative, then this expression is less than 1 and your sub-threshold swing goes below 60 millivolt per decade. And where do we get this negative capacitance? So first let's see this charge versus voltage or energy versus charge. You can see this is a positive capacitor. If it is inverted, both on these both of these plots, so then it will be a negative capacitance. And where we can see this energy charge or polarization curve is in the ferroelectric material. So in the ferroelectric material, you see this double well curve where you have this region where the capacitance is negative. So the paraelectric, as we said, PE curve is this straight line where there is no polarization when electric field is removed. In case of ferroelectric materials, you see this conventional hysteresis, and there are two possible states of polarization. And where do we get this ferroelectric? Why do we have, or how do we get, is because of the non-centrosymmetry. So as we apply the electric field, this one moves up or down, correspondingly giving you non-zero polarization at zero electric field. So for modeling or in terms of understanding this mathematically, there is a Landau-Coulomb theory of nonlinear dielectrics. So where the free energy is given in terms of this polarization curve, and generally these alpha beta can be positive negative, but gamma is taken positive for stability. And we also have the dynamics where we can have the time variation of this G, but a steady state we can easily put it 0. So we have this relation between electric field and polarization. And from this equation, if you solve, we can easily see that for alpha greater than 0 at E equal to 0, there is only one root, that is a paraelectric material. And if alpha is less than 0, then at E equal to 0, there are three roots. That is for a ferroelectric material. So there are few assumptions which are made in this thing, which so now next let's see. We said three roots. So of course one or two of these are on the hysteresis curve, which we are seeing, which were there, and one is this one, which is what is interesting. So we can see that P equal to 0 is not possible in the isolated, because you know it's coming at the maxima of energy, and that's unstable region. So, but at the same time, this is the region of interest for negative capacitance. So now if we can somehow stabilize this region, then we can go through this part, which is the negative slope or negative capacitance region. And if we apply the electric field, we can easily see the in terms of paraelectric, we are going to move on this. In ferroelectric, this double well curve will change as shown in this from A, B, C, D, E, F, depending on the electric field direction we are applying from, starting from this side to this side and then this side. Normally, we know that this region is unstable. So if we reach this stage, this point, then it will this point giving you hysteresis. When we come from this side, you can easily see this will go through this hysteresis curve, and then we are not going through this negative capacitance region. So how we can stabilize this negative capacitance region, which is falling at the energy maximum? So if we can add a dielectric along with this ferroelectric, ensuring that our capacitance total is maximum, then we can stabilize this. So there are these equations which are, if you go through and solve this, what we finally get is that if the total capacitance of the system is positive, then this system is able to work even if we have the negative capacitance region in the ferroelectric. And that is to say that your absolute value of ferroelectric capacitance must be always greater than this dielectric capacitance to ensure a stable system. And this is also given by Asif Khan's paper, where they demonstrated this. Yes, you will get this. Now, is it only theory or experimental? Well, there have been several demonstrations. I'm showing you only two of these, where they showed that if you have two of these materials, let's say a dielectric and ferroelectric in series, the total capacitance was more than the dielectric capacitance. That means there was a signature of negative capacitance. So that established that experimentally there has been demonstration of this negative capacitance. And then there have been a lot more demonstration in different papers using ferroelectric resistor system, and more recently in this Nature paper on the demonstration of this negative capacitance and also this S curve, which is the negative capacitance region. So with that, and this was how they measured this S curve. There were more details. So that's having said that, people have demonstrated this experimentally, the negative capacitance effect. Then there have been a lot of papers on negative capacitance transistors, especially this one, where for the first time hafnium zirconium oxide was shown to have ferroelectric properties. And that one is very promising because hafnium oxide is already used in the CMOS line, and then this is very much compatible with the conventional CMOS process. So now let's try to study the modeling properties. So there are two types of structures in NCFET or negative capacitance transistor. One is the metal ferroelectric metal insulator semiconductor. That means this ferroelectric is connected by a wire with the transistor, normal transistor, any transistor you can take. So there is this metal layer in between this. And there is this MFIS where there is no metal between ferroelectric and dielectric. So ferroelectric is directly on top of this dielectric. What will be the difference between these two? Difference is this internal voltage in this case is constant all over the MOSFET, this metal plate. In this case, this Vint or internal voltage is going to vary from source to drain because of the polarization of this ferroelectric. So now let's first start the simple structure, which is the MFMIS. That means there is a metal here. So you can see this FinFET structure where there is a FinFET. On top of FinFET, you have this ferroelectric, which is there. And you have this internal metal, which is equipotential all over the place. Okay. In terms of showing it symbolically, this is to say that there is this FinFET, and on top of that we have connected ferroelectric capacitor, and then you have the gate terminal. So this internal metal gate is going to make sure that we have equipotential surface, and that means there will be especially constant internal voltage Vint, which is this one. Okay, and then we can easily consider these two, that means FinFET and the ferroelectric, as two separate quantities for modeling purpose. So this is how we start with. We are going to model this separately, and connect them together. So first we experimentally calibrate the Landau model using the experimental ferroelectric properties, and then from that we extract the alpha and beta parameters, and then we calibrate the FinFET model. We are using BCM-CMG industry standard model for FinFET, using this 22 nanometer FinFET. And then once we have both of these, that means ferroelectric as well as the FinFET parameters, we go and implement these two models. That means the LK model of ferroelectric in a Verilog A code, and also the BCM-CMG model in Verilog A code. And we connect these together such that SPICE will solve these models self-consistently. There is a catch here that Landau model needs charge, and we need to pass the charge from the CMG FinFET model Verilog A code to this model. So there is a trick involved which we have to use such that we also pass the charge other than the voltages. So here are all the equations which are used. This is the internal capacitance. Internal means the capacitance looking from the gate of the FinFET, and there is this quantity which is of interest, that is the internal voltage gain. That is how much change is there in the internal voltage del Vint when we change the gate voltage, and this is given by this mod CFE by mod CFE minus Cint. And you can easily see that if CFE is close to Cint, then this change in Vint is going to be very large compared to the change in gate voltage, and that's what the property we would like to use. So here I am showing you the capacitance matching. This pink line is the FinFET capacitance, and we very well know this is a conventional gate capacitance which is shown. And this is the ferroelectric, these are the ferroelectric capacitance curves shown for different ferroelectric thickness. So you can see that as we are increasing the ferroelectric thickness, the matching is improving. But at some point of time, or for some ferroelectric thickness that is 14 nanometer, this capacitance is less than the gate capacitance. So that is the unstable region which we talked about. And same you can also see here for the internal voltage gain, that as we are increasing the ferroelectric thickness from 8 nanometer to 11 nanometer, we are getting the larger internal voltage gain. Also, this drain voltage will affect the capacitance matching, because the Cint is a function, that means gate capacitance is a function of drain voltage. So we have to be careful whether we are able to get the capacitance matching for all the drain biases or not. We have to check that. So now let's analyze how this affect the current voltage characteristics. So now let's look only into the subthreshold region. This is these curves. You can see this pink is what is for TF equal to 0. That means our normal FinFET without any ferroelectric, which has some subthreshold swing. Now, as we increase the ferroelectric thickness, you can see subthreshold swing improved. But at some point, you start seeing the hysteresis. And that's when our system enters into the unstable region. This is the plot which is shown here. You can see that subthreshold swing is going all the way from starting from 70, but it goes down to low value as we increase the ferroelectric thickness. And why is that so? You can easily see it from these equations, that as and when we have the better matching of this capacitances, we are going to get the better subthreshold swing. Next is this on region, these plots, where this pink is for no ferroelectric material, and then as we have the ferroelectric thickness change, we can see the on current is improving. And why is it? Because you can see this from this equation, the capacitance matching is getting better, so voltage gain is there, and voltage gain is giving you the higher on current. So that's what is really amazing in this device, that not only your subthreshold swing improved, but also on current is also improving. And this has been demonstrated experimentally in several papers with smaller subthreshold swing values as well as the higher on current value. So both of these have been demonstrated experimentally. And now coming back to our analysis, now let's look at how the IDVD characteristics look like. So here you see that IDVD is more conventional up to some point, but then you see that it starts reducing as we increase the drain voltage. And that is because your Vint is reducing with VD because of the disturbance in capacitance matching caused by the drain voltage. Okay, and that is causing you or giving the lower current at higher drain voltage. So this is again very interesting, because now you are seeing this negative differential resistance in this device. Another interesting property in this device is the dibble is negative. So conventionally, we know that as we increase the drain voltage, our threshold voltage is going down. In this case, it's opposite. As we increase the drain voltage, threshold voltage increases, and that is causing reduced off current. So here is the dibble plot versus TFE, that as we increase the TFE ferroelectric thickness, dibble starts from positive but goes into the negative region. So that again is very useful. That is to say that off current is increasing, but still you have higher on current, and higher on current is, as explained earlier, is coming from the capacitance matching. And this we have also checked using numerical simulation. The region for this change is, or the increase in threshold voltage is, that as we increase this drain voltage, you can see that the barrier height increases. Okay, and this increase in barrier height gives us the larger threshold voltage or negative dibble. And then for high VDS characteristics also we have plotted here. We see that there is a hysteresis when mod CFE is less than C, this is the unstable region. As TFE is increasing, the subthreshold swing reduces and I-on increases, and I-off also reduces for high VD. So that's really interesting. You have all the goodies which you would like to have. Also, this width of hysteresis at large thickness can be controlled with drain bias. So that's another interesting property we see in this device. And then if you see here earlier, when we actually first published this negative differential resistance, there were no experimental papers, but then there are a lot of papers which showed experimentally that NDR is there in these devices. And then we also showed here that you even start seeing hysteresis on IDVD curve if you are using sufficiently thick ferroelectric material. So that's again quite weird and interesting plot of IDVD in NCFET. So, you know, when we optimized all of these, what we are seeing that we started with this red curve, which is for 22 nanometer node FinFET, and using the negative capacitance properties, the NCFET is giving us here much larger current. And if we want to have same ion current, then we can easily reduce the VDD to half. So here you can see at half VDD, we still have the ion same as it was for 22 nanometer baseline FET. And along with that, we also have reduced off current. So these are the promises which this technology is giving in terms of the negative capacitance transistor, why it is so much interesting and useful if it comes into the production. And then we have done a lot of studies here in terms of material variation, how it is changing. So here we are seeing that, okay, what if we are able to tune these PR characteristics and EC characteristics, which is the remnant polarization and the critical electric field, or this EC. So it seems that low PR and high EC is going to reduce the CFE, which leads to improved capacitance matching, and that's giving us a high gain. Also, it will give us low subthreshold swing, and there will be increased ion but reduced I-off. So that means ion by I-off will be much better. And then we have worked on modeling of this MFIS, where there is no internal metal. Earlier we were talking about there was internal metal here, but since there is no internal metal here, we cannot separate out these ferroelectric and the transistor into blocks. So now we have to self-consistently do something or solve or simplify these equations. So we play with these, we start with the conventional equations, but then we have to couple these together, solve them analytically, and then finally we have all the models. So we start with this, we solve this, we play with this, and then we see that okay, we are getting very good characteristics using this model, including the experimental validation shown here. And we also compared the MFIS versus MFMIS, where we see that our MFIS, that means no metal, is giving you a smooth hysteresis compared to MFMIS. And that's because in case when you have a metal, internal metal, all the dipoles are going to switch in one go compared to the MFIS, where there will be the switching of dipoles will be one by one from source to drain. And then we have also worked on gate-all-around negative capacitance transistor. Again, a detailed model derivation. I'm not going through it, but we also validated it with the numerical characteristics and the model. And you can check the publications for more detailed mathematics. And then we also did an interesting study on comparing this MFMIS versus MFIS, a long channel, using this segmentation approach. And that also showed us the characteristics which we were seeing earlier. And here you can see both give you better characteristics, but in terms of long channel, MFMIS is giving better because, as I said, all the dipoles switch in one go, and that's why it is giving you better characteristics. And there are a lot of interesting properties. For example, these hysteresis which are coming there for different drain voltages. And then we did also numerical simulation study. So here we have compared these transistors properties in COMSOL. So interesting is this curve VT versus L. For normal transistor, you can see that VT goes down, but in these transistors, it goes up, which is more like a hump-like characteristics coming from which is there in the in conventional transistor when we have halo doping. And same is true for subthreshold swing. And the origin of this is actually in the fringing field, which is there in the corners near source and drain. So given the time, I will not go through the details, but we do see these humps on this conduction band near source and drain, which give us this interesting property. And then also the reverse subthreshold swing scaling is reversed. So this is, you are seeing that our subthreshold swing gets better as we reduce the channel length. And also we have studied how the impact of spacer permittivity is. So as we increase the spacer permittivity, our threshold voltage as well as subthreshold swing both gets better, and even dibble gets better. And then we also did the study in subthreshold region. Similar properties we observed as we shown earlier. And also here we see that if the source drain doping is increased, again we get the better characteristic because of increase in the fringing field. So now just let me show you this, that experimentally also this has been demonstrated that NC-FET are going to work at a very high frequency. There is no issue as such, which is sometimes a concern for people. And we have studied also the circuit characteristics. Here we again are seeing interesting. We see the hysteresis here in the VTC curve, even if there is no hysteresis in the IDVD curve, again coming from the NDR characteristic. And then we also studied the SRAM characteristics. And then we did this interesting study for the entire standard cell library on 7 nanometer node FinFET. You can see that for the baseline here, a lot of our occurrence is for gate delay around 20 picosecond. The peak is here. But if we are using NC-FET or the ferroelectric, our gate delay is much more concentrated and at a smaller value. So that is what is interesting, that our delay will reduce if we use this NC-FET in the standard cell or the processor. And then we did the three studies here, that what is the frequency increase due to NC-FET under same voltage constraint here. So if we take these two voltages, then we see that we can increase the frequency for different ferroelectric thicknesses. And larger the ferroelectric thickness, more the frequency increase. And then there is this, what is frequency increase under same power density? We still get good increase in frequency. Another is what is the minimum operating voltage along with achieve power reduction under same performance. So again here you can see we can reduce the operating voltage for larger thickness and still get the power reduction of close to 50%. Very promising characteristics at the library and processing. So just before I conclude, there are a lot of open questions in this device. Still we are asking, is negative capacitance a static or transient phenomenon? Lot of papers are there, no conclusion. What is the physical origin or explanation of negative capacitance effect? Still debatable. And then there are a lot of these second order effects, multi-domain effects, multi-grain effects, impact of traps, etc., reliability, which needs to be studied. And even for circuits, what will be the impact of this negative differential resistance and negative dibble, and how the circuit designers will cope up. So to conclude, the maintaining ion by I-off is biggest challenge in the new technology nodes. Negative capacitance is one of the best choice. Most probably we have a good material for ferroelectric materials, so this is hafnium zirconium oxide. Integration still remains a challenge, but good progress has been made. And SPICE models are ready for circuits evaluation so that we can do the early circuit evaluation. That's it. Thank you. I can take questions.
Yeah, so thank you, Yogesh, for nicely summarizing all this exciting work. So if there are any questions, you can type in and I can ask to Yogesh. So probably it may take some time. I don't think audience will be kind of in this online mode, but I have a small question, Yogesh. See this all-around gate transistors, gate all-around transistor. So are they experimentally fabricated, and if so, are they vertical ones or horizontal ones? Can you just briefly put some light on that?
Yes. So first, your answer to your first question is that experimentally there have been lot of demonstrations of both vertical and horizontal. I can tell you that vertical gate-all-around transistors have been already in production for quite some time. I will not give you the name, but I can,
Yeah.
they are used in memories. And the horizontal ones are promising and being explored for logic devices. So this horizontal, which we call sometimes also either gate all around or nanowire or nano seed transistor, lot of papers are coming in last 2-3 years on this, and Samsung has already announced that they will bring it in the 3 nanometer technology or 5 nanometer technology.
Okay, okay. I think yeah, it gives a clear answer and very good. So thank you, Yogesh, for this nice talk and being part of this prestigious conference. Obviously, it gives us strength. So with this, I think we all will thank Yogesh, because I don't think there are any other questions, and we'll go to the next talk. So thank you, Yogesh.
Thank you.
Yeah. Thank you. So the next talk, I think, is slightly changed. The first, so originally it was by, let me just look at it. So originally it was by Dr. Manoj Kumar, postdoctoral fellow IIT Delhi, but somehow because of some incidents, he is not able to join us. A talk from morning session, who is by Miss Shraddha Pali, is again scheduled at this time, and she will be presenting on optimization of drain extended MOS devices for reliability in high switching applications. So Shraddha, if you are around, you can share your presentation. So let's welcome Shraddha. Shraddha, please go ahead.
So should I share my slides?
Yeah, please share your slides, and yeah. Yeah, it seems perfect. You may please go ahead. Start, please.
Good afternoon, everyone. I'll be presenting optimization of drain extended MOS devices for reliability in high switching applications. The outline of this presentation includes research background, objective, and basic DNMOS structure as power device. The switching optimization limitations and reliability trade-off are discussed next. Conventional DNMOS structures and its types are presented. 2D simulations are done to discuss device physics, electrical characteristics, and transient analysis. The objective of this research is to reduce the gate charge and improve switching performance. DNMOS is drain extended NMOS and finds application in interface circuit design. In this work, two conventional DNMOS with and without shallow trench isolations are used for optimization for switching performance. The conventional DNMOS has large gate footprint, and this has increased its gate charge and coupling capacitance, which has limited its switching performance. So in proposed device, the gate footprint has been scaled, and optimum suitable gate edge termination technique is applied so as to ensure safe operation in high field regions. All the simulations are done using Synopsys 2D device simulator. So this is the basic DNMOS structure. This is drain extended N-type MOSFET. It's a power device. It can support low gate voltage across its thin gate oxide, and large drain voltage is supported by its drain region. So in comparison to a core MOSFET, this DNMOS has an extended drain region which has a low doping so as to support the large drain voltage and reduce the stress across the gate oxide near the gate drain edge. Now switching performance, when we improve the switching performance, there may be some reliability trade-offs. So the switching performance is defined by two important parameters, delay and switching loss. Delay is directly proportional to gate charge, and switching loss is defined by a figure of merit, which is a product of gate-to-drain coupling charge and on resistance. In high-frequency application, switching loss becomes a very critical parameter as it can become higher than the conduction losses. Next is reliability. Now, reliability is defined by safe operating area and hot carrier injection, and both these factors are dependent on the generation of impact ionization generation rate and its location within the device. Now, gate charge optimization. The gate charge optimization can be achieved by reducing the gate footprint. As it can be seen in this DN-MOS cross-section, it comprises of two parts, an intrinsic MOS with a drift region which is in series like a resistor. So if we reduce the channel region to reduce gate length, in that case, the punch-through breakdown will limit the device performance. Whereas this overlap region behaves like a fill plate, and if we optimize this region to improve device switching performance, in that case, some high fill effects will come up, like there will be electric field near gate edge, which will increase the impact ionization rate, and subsequently hot carrier injection will result. So the solution to suppress all this high field effect is to use an effective gate edge termination like P-top near gate edge. Now this is the conventional DN-MOS STI and non-STI devices which has been used in this work. These are thin gate oxide devices fabricated using 65 nanometer CMOS. It uses N-well and P-well in standard CMOS process as drift and body region. A shallow trench isolation is added to improve the gate oxide reliability. Same process flow has been used for both these devices, and these are realized using a well-calibrated process simulation deck. The simulation result analysis is categorized into three parts. The first case is the conventional device, where both non-STI and STI device with a large gate extension of 200 nanometer are compared. In next case, the overlap length has been scaled down without any edge termination so that there would not be any surface modulation. And the third case is the proposed device, where we have the small gate with P-top, that is a P-type pocket near gate edge as the edge termination. In all the devices, source to drain pitch and other layout parameters are kept constant. Now this is the conventional device. In this device, we have a large LOV, and this have fill plate effect over the drift region. This can effectively modulate the surface potential, as well as it can increase the accumulation in the drift region, which reduces on resistance. So these devices provide a good R-on and BBD trade-off. As it can be seen here, in presence of large overlap length, potential line scrodding is relaxed and lateral field is also relaxed, and the peak impact ionization location is inside the bulk away from the gate oxide interface, both in non-STI and STI devices. The only drawback of this conventional device is the large gate capacitance and coupling charge. Now this one is the second case. This is the intermediate device where we have reduced the gate footprint, but we have not added any kind of edge termination. So the footprint has reduced, the gate charge is reduced in these devices, but in absence of any edge termination, we can see there is a crowding of potential lines across the gate edge, which has increased the lateral field, and this has resulted in a large peak impact ionization just below the gate edge in both the devices. So the reliability, oxide reliability is compromised in case of both STI and non-STI devices. This is the final proposed device. In these devices, the scale LOV is in conjunction with P-top, that is the edge termination, both in non-STI case and STI case. Now, addition of P-top can effectively modulate the surface field. It can support the large drain voltage and improve on-state breakdown characteristics. As we can see here, the surface potential lines are relaxed, and again, they have effectively reshifted the impact ionization location deep inside the bulk. Now these are the output characteristics of devices. The first plot compares the conventional device with gate scale devices. As it can be seen, in both STI and non-STI case, When gate length is reduced to 50 nanometer, from 200 nanometer to 50 nanometer, there is a step rise in drain current at high drain voltage. The SOA, that is the safe operating area of both these devices, is reduced. The reason for this step current increase is substrate current induced bias effect, where at high drain voltage, the increase in substrate current has resulted in threshold voltage degradation of intrinsic MOS and drain current has increased. Next plot shows the optimized device with the conventional device. And here we can see that addition of p-top as H termination has effectively suppressed the high field effects, that is the step rise in current has been suppressed. So SOA has been enhanced in presence of p-top. Next characteristics are substrate current. Now substrate current characteristics with respect to gate voltage are plotted for all the cases, and we can see that in absence of H termination, there is a large increase in substrate current peak at lower gate voltage. Hence, the gate switching reliability is highly compromised in this case. However, when we add H termination, the suppression, the increase of peak has been effectively suppressed both in non-STI and STI devices. The final analysis is the transient analysis. In this case, gate charge and inverter circuit switching delay are calculated. Now, gate charge is basically calculated. A gate charge and the coupling charge are calculated using this curve. As it can be seen here, the time taken by the gate voltage of this test circuit to reach the desired drive gate voltage is the total amount of gate charge, and there is a large decrease in gate charge of the optimized devices. Similarly, this flat region, that is the plateau region, corresponds to gate to drain coupling charge, and there is a large reduction in coupling charge in case of optimized devices. Next is the switching performance of inverter circuit, and the output switching delay is effectively reduced in both the proposed devices, STI and non-STI, as shown here. The switch devices are tabulated here. It can be seen that in case of proposed non-STI devices, there is a large degradation of on resistance due to the presence of p-top. However, the improvement in gate charge is also very high, and the net improvement of figure of merit is high enough to apply this technique in our device. The delay is also improved by up to 20%. In case of conventional and proposed STI devices, the presence of STI has reduced the sensitivity of on resistance with variation of gate length, and hence the on resistance degradation is very low in this case. This is only 26%. However, the gate charge improvement is still very high, and we obtain a large figure of merit improvement in case of proposed STI devices. The delay improvement of 21% is obtained in these devices. The summary of the work done in this paper are as shown below. The proposed DNMOS transistor in the proposed DNMOS transistor, we have done drift region engineering by replacing the gate extension with the p-top as H termination. The total gate charge is reduced by more than 50% for both STI and non-STI devices. Gate to drain coupling charge is reduced by more than 60% in both STI and non-STI DNMOS. They have high switching performance without compromising on DNMOS SO and gate oxide reliability. Figure of merit improvement has reduced the switching loss, and transient switching performance has also improved. Thank you, everyone.
Yeah, thank you, Shraddha, for nicely summarizing this whole talk in time. I'll request the audience to kind of ask any questions, the members who are attending. So, okay, so I think there is a question. Let's see. For the 7 nanometer device NCFET, I think this was for Professor Yogesh Chauhan. So maybe you can just write to him, Monika Sharma. Your question was 7 nanometer device NCFET. How much should be the thickness of the ferroelectric layer? So maybe I think we can just get his answer right away, Yogesh. So Monica wanted this thickness of ferroelectric layer, or maybe she can write to you. So for this current of, yeah, if you are there. So I somehow missed this question from the previous talk, so you can probably I'll just type it. So for this talk, are there any questions from attendees? Shraddha, maybe you can just highlight in one line. So the devices you are simulating. So are
Yes,
there
sir.
experimental validations of the studies you are doing, or it's?
So I have done the simulation work, although experimental results are also available for those devices.
So you have calibrated with the experimental.
Yes, sir. Yes, sir.
And do you think these devices will be soon coming into chips, or is it like exploration of certain?
So actually, this was basically the idea of this work to study the implementation of techniques on devices. So
Okay.
I did the simulation to identify the improvement which can be achieved.
Okay. So very good.
Maybe I'll
So
ask a
yeah.
question.
Yes, sure.
This is Professor Mayank Shastri from Icee, Bangalore.
Yes, sir.
So quick question, how did you investigate the SOA behavior? I mean, how did you simulate this?
So SOA, sir, I have associated the SOA with the rise in drain current in the IDVD curve. I mean, this my SOA was related to this IDVD curve.
Okay, so that was not a failure simulation.
So I did.
That was on-state breakdown.
Yes, sir, on-state breakdown.
Okay, thank you.
So if there are no more questions, maybe we'll go to the next talk. So thanks, Shraddha, for kind of presenting this nice work and also summarizing in time. Thank you so much.
Thank you, sir.
You can, yeah. So next speaker is Mr. Sankatali Venkateswarlu from IIT Hyderabad, and he will be presenting on device SHEs in the presence of a non-equilibrium channel heat transport in SOI and SOD FinFETs with technology scaling. So you can please share your slides.
Thank you, sir. So I'm sharing my. Is it visible, sir?
Yeah, it's visible. It is perfect. I think you may please start now.
So good afternoon, everyone. So my presentation is like the topic of the presentation heat transport with technology scaling. So the outline of the talk is introduction, followed by numerical device design and the simulation methodology we used. And after that, we'll be discussing the simulation results, and in that we'll be discussing about how the thermal conductivity is computed using the non-equilibrium channel heat transport, like Von-Boltzmann transport equation model. And channel thermal conductivity of 40 nanometer SOI and SOD FinFETs will be investigating. And after that, device self-heating effect with the technology scaling, how it is affecting with the technology scaling. And we'll be introducing a new technology like silicon and diamond FinFETs. And after that, we'll be discussing performance of flexible FinFETs with ambient temperature. So let us start. So basically, introduction. So first, FinFETs at 22 nanometer, so having major breakthrough compared to planar MOSFETs because of better electrostatic integrity and higher drive currents. So however, with further scaling the FinFET, so like sub 10 nanometer logic, so we industry opt for a thinner and taller fins, so to improve the drive current and electrostatic integrity. And so to reduce the source drain parasitic resistance, so the industry move for the source drain region doping higher value like greater than 10 power 21 per centimeter cubes. But however, the electrothermal performance is getting degraded. So this is mainly due to reduction in the fin channel thermal conductivity. So it is mainly due to enhanced phonon boundary scattering effects of the thinner fins and enhanced phonon dopant scattering, so because of higher doping. And after that, decreasing phonon mean free path. So due to Umklapp scattering process at higher temperature, that will happen due to self-heating effects. And these will result in transport from channel hotspot location to the terminal electrodes. So in this work, we investigated the thermal conductivity by using the Phonon-Boltzmann transport equation with the relaxation time approximation in TK. And this is the device figure you can see in the figure. So the proposed FinFET for the 14 nanometer technology and the physical parameters you can see for the 14 nanometer technologies. And the calibration results you can see that for calibration we have considered the 3D drip diffusion model, hydrodynamic and thermodynamic models, and the advanced carrier mobility models we used are doping dependence and immersion and accumulation layer mobility model, and high field saturation and ballistic mobility. So for calibration, we mainly tune these two parameters, high field saturation velocity parameter such as VSAT 0 and beta value, and then ballistic mobility parameter also we have tuned, and high K mobility degradation. So as we are using high K dielectric materials, so the mobility will be degrading in the channel region due to high K dielectrics, such as remote phonon scattering and remote Coulomb scattering. So after that, for electrothermal analysis, we have considered thermal boundary conditions for electrode and non-electrode surfaces. After that, so we invoke the Phonon-Boltzmann transport equation, which considers the thermal conductivity dependence on doping temperature and thickness. So these are the expressions from the Phonon-Boltzmann transport equation. So you can see the thermal conductivity in the equation 1 and from the heat capacity. You can see in the equation 1, so the relaxation time. So we'll be approximating the relaxation time based on the temperature, depending on temperature, doping, and thickness. Equation 3 to 4 depends on temperature. You can see it's a strong function of temperature, and also you can see in the doping dependent. So you can see the parameters. So mass of the doped atom and radius of the doping atom, like size of the atom. And after we invoke the thickness dependency also. You can see the DLY means layer thickness in this equation 9. So we invoked all these models combinedly and then device thermal conductivity and how it is affecting the device self-heating effect investigated. And you can see in figure here, you can see the channel thermal conductivity as a function of fin width. So you can see when you scale down the fin width, so the thermal conductivity is getting decreased. You can see when scaling down from around 50 to like 1 nanometer, so 20 times it's got reduced at constant doping and temperature. You can see in figure B, so it's as a function of doping. So up to some the increasing doping. So initially it is maintaining constant, but at 10 power 19 per centimeter cube, so the thermal conductivity is drastically is decreasing. So start decreasing, and you can see more when you go up to some 10 power 22, so it is degraded by 10 times. It is decreasing. Also, you can see in the temperature. So when you scale increase the temperature. So initially, when increasing from absolute 0 Kelvin, so it is the thermal conductivity is increasing. So this is mainly dominated by heat capacity, because of heat capacity will be increasing. So that's why the thermal conductivity is decreasing. But at around from 250 Kelvin, so this is mainly dominated by phonon relaxation time, which is inversely proportional. You can see, so from these results, so we can say that suppose if you take a FinFET, so the FinFET, the channel doping is less, so that's why, and the thickness is very less. So that's why in the fin channel, so the thermal conductivity is mainly dominated by the thickness. But in the source drain region, so the KTH is reduction is mainly dominated by the doping. So, but however, the temperature, temperature is dominated in both source and drain regions, so channel and source drain regions. So you can see then the figure thermal conductivity for SY and SOD FinFETs. So you can see in figure A and B, so SY FinFETs. So without self-heating, if you see the thermal conductivity in the channel is a bit higher, but in the source and drain region, you can see is decreased. This is mainly due to decrease in the doping, increase in the doping. So you can see self-heating effect, so it's got reduced in the channel. So you can see the cut line plot over here. So in figure E, you can see the 13% decrement to in source drain region compared to the channel. And you can see it's further degradation. You can see in channel mainly the degradation is more in the channel region. You can see in source and drain region also is getting degraded. If you use SOD technologies, So you can see that the lattice temperature is slightly reduced over here compared to SOI technologies. So that's why you can see with self-heating effect. So the degradation in the thermal conductivity is less. You can compare to SOI case. That's why it is 18% decrement. Also, you can see in the source drain regions also slightly reduced. So that means if you use SOD technology, so the thermal conductivity is slightly improved, and also you can see the heat flux also is increasing towards substrate. So that's why overall results in lower self-heating effects. We also investigate the impact of technology scaling. So how it is affecting. So when you scale down from 14 nanometer to 7 nanometer. So you can see that the thermal conductivity is decreasing. You can see 12 from 14 to 10 nanometer. Again from 10 to 7 nanometer, 8 point or so close 9% decrement. So this will result in increasing the device self-heating effect. You can see the delta TL maximum is increased. So that means TL maximum is 300. So this value is increased by 2.5 times and 1.3 times from node to node, like 14 to 7 nanometer node. Also silicon and diamond FinFET. So we investigated the technology scaling. You can see generally if you place a diamond material over here, so the more heat flow will result in a lesser hotspot in the channel region. So you can see scaling down from 14 to 7 nanometer. So the delta TL maximum is improvement, decrement is improved. You can see from 1.4 to 1.6 from 14 to 7 nanometer now. You can also see the heat flux distribution in the SOD technology case. So the heat flux is more towards bulk substrate, which results in reducing device self-heating effects. And then so we have also investigated the impact of self-heating effect on like off-state performance. In general, it's increasing the device temperature, so that will increase the device ambient temperature. So here we investigated with increasing ambient temperature how the off-state and IM by IF ratio is increasing. Improving. In general, it will be increasing for SOI, both SOI and SOD cases. But you can see for SOD cases, so this implement using the off frequency for SOD. Also, you can see improved. You can see 16% improvement in ion to IF ratio. So we investigated the electrothermal performance SO and SOD FinFETs through the estimation of device lattice KTH degradation and device self-heating. The impact of technology scaling from 14 to 7 nanometer on device electrothermal performance, which reveals that channel KTH is ready and results in more device self-heating effect. And introduction of SOD technologies results in improvement in device electrothermal performance by exhibiting lesser channel thermal conductivity reduction compared to SOI technologies around hotspot location. We can also see that improvement in logic performance by lowering the IF current, which results in increasing the ion to IF ratio. And therefore, we can say that SOD technology based FinFETs can be aggressively downscaled to sub 10 nanometer technology, so better electrothermal performance. Hello, sir.
Since there are no questions, yeah, please. Please, if there is any question, you can directly ask. So I think it was just some noise. I thought there is a question. So anyway, we welcome you for this good presentation, and then we'll, because of sake of again keeping time, probably. So I request the members to write to you in case there are any suggestions or questions to your email ID. So we'll go to the next talk, which is final talk. Okay. So I think if there are no questions, I had not unmuted myself. So if there are no questions, we'll for the time we'll go to the next talk of this session, which is the last talk. That is to directly. Yeah. Please unshare the presentation. So thank you so much for presenting in time and kind of sharing your work with us. So we'll go to the next presentation now, which is so you can unshare the slides. Mr. Venkateshwarlu.
Yes, sir. I have unsaid. One second.
Yeah. So I thank you again on behalf of ICEE organizers. And the next talk will be by Mr. Ankur Singh from IIIT Guwahati. Based quadrature oscillator. So Ankur, if you are available, please share your slides. In the meantime, see, this question answer session is not very practical in online. So you all may try to write to the presenters if you have any specific questions or suggestions. So you can write to their email IDs, and email IDs you can also, if you don't have, you can take from volunteers or organizing side. So that option is there. If there is some exciting suggestion or question, you can play to it. So Ankur, you please share your slide. So is Ankur available?
Sir, I don't see him in the participants list. Meanwhile, can we share Dr. Manoj Kumar's presentation till he joins?
I think that will be so. Maybe you can just at least introduction part, some crucial aspects of the work and conclusion. So maybe in next 10 minutes, you can one of you you can share and maybe go through.
So we just have the presentation from him. We do not have any update. So maybe we can. I ask Pragya Kumar Kaushik to share the slide and maybe announce the title of the talk as well.
Yeah, and I request one of you to go through the slides, scroll through the slides,
okay.
So that and you can just briefly mention, just as a kind of you can say go through the slides quickly, so that.
Okay. Yes. Okay. Pragya, kindly take over.
See, Akansha, I think you yourself can maybe go through the slides and just read the kind of titles of the slides, and maybe you can scroll through this if possible.
Okay, sir. Let me share. I think there is problem with Pragya's screen. Let me try.
So I think we have got a volunteer. Akansha will be going through the slides, and yeah, Akansha, you please start.
Yes. Is my screen visible?
Yes, it's visible.
So this talk is based on the effect of self-heating on linearity of novel junctionless accumulation mode negative capacitance FinFET. And the orator is Manoj Kumar, who is not able to present himself due to some accident. So I'll just go through the slides by stopping at this slide for some seconds. Shall I read out the objectives, or I let the audience to read?
Akansha, I think you can 10 seconds you can stop and just say that these are the
Okay.
objectives and so on. So you finish the
Okay.
presentation maybe in
Okay. Okay, sir. Okay. So this is the outline of the talk. This slide shows the MOSFET scaling and thermal effects. Followed by self-heating issue in MOSFETs. This slide shows the JAM NC FinFET. The effect of self-heating on transconductance. Results and discussion. Which is continued in this slide as well. Then analytical model for self-heating. Finally, the conclusion. And that's all.
So thanks, Akansha, for finishing this presentation. And I think with this will, because Ankur is still not there.
Yes, sir, I still cannot see him.
So I think this will end this session itself. And I thank all the invited speakers as well as the student contributors and PhD students, attendees who. So if there is any additional input I can share with people, or will formally close this session. So any volunteer can suggest. Akansha, again.
Thank you, sir.
Yeah, yeah.
Okay,
So
thank you.
thank you all. Thank you all for joining, and hope you enjoy other sessions. Thank you so much.
Thank you. Thank you, sir.
Thank you, sir.
Thank you, sir.
itu mute no mute
Good evening to one and all present there. So shortly we will commence the poster session. In this, each speaker or each poster will be given 5 minutes to present your poster, and from our side we will be displaying your poster. We will be sharing our screen of every participant poster one by one once the name is called out by the uh, our invigilators. So you just have to take 5 minutes to explain your poster, then the evaluator will evaluate your poster. So here Dr. Amit Jaiswal sir and Manoj Verma sir will be evaluating all your posters. So we will start with one posters from the first name. Jaiswal sir. Amit sir. Amit sir.
Hello.
The first poster is from Sat. Yes, sir.
Hi, I'm Satyajit Das. Hello.
Yes, yes, sir. So first poster will be from Satyajit sir. You have 5 minutes to present yourself.
Okay. Thank you, sir.
Yes, just a minute, sir. I want to confirm whether Amit sir is.
Okay.
Sir, yes. Amit sir, can you hear me?
Yes. Yeah, I can hear you.
Yes, yes, sir. We'll start with the first presenter.
Sure.
Yes, yes. Please, Satish, just. Yes.
Thank you, sir. May I start, sir? Hello.
Yes, sir. You can start, sir.
Good afternoon, all delegates present in this Icee 2020 conference. So my presentation will be on the optimization on the copolymer based interdigital sensor capacitive sensor structure. Actually, nowadays the polymer based sensor are the emerging trend in the sensor technologies. So the main objective of this work is to optimize the sensor structure so that we can have maximum we can have the output which can be altered by the geometrical parameters of the so the hello, is it audible, sir?
Yes, sir. Yes, sir.
Yes, go ahead.
So these IDC sensors, they are based on this IDE structure, interdigital electrode structure. So in this structure, we can coat our sensing layer, which in this case it is in polymer. We can coat it over the interdigital structure or in between the two electrode structure. Mainly, sir, I can go. Hello, the figure actually. Thank you, sir. So, in this ID structure, the main objective is to vary the geometrical parameters of this ID so that we can have the maximum output in terms of its sensitivity and the capacitance. So, in figure 1 it represents the ID structure. The figure 2 it represents the ID structure where we give the analyte, and this analyte will absorb and adsorb by the sensing material. And this figure 2 it shows the equipotential surface which are denoted by this V naught. Now, in the figure 3, it shows how this capacitance, it shows the capacitance structure actually, the capacitance of the outer corner electrode with the equipotential surface and the internal capacitance and the capacitance between the electrode and the substrate for the substrate with the equipotential surface. So the capacitance of sensor output is a combination of three types of capacitance. One is the corner capacitance, one is the summation of corner capacitance plus the capacitance between the internal electrode with the equipotential and the substrate capacitance. So the equation shows CC the corner capacitance. These equations are based on some existing formulas for deriving the capacitance of this ID structure. Second equations, it shows the capacitance C, which is twice of this corner electrode capacitance plus n minus 1 the internal electrode capacitance. Normally what happens if the number of electrode structures are more than 100, approximately 100, in that case we can neglect this corner capacitance effect CCC. But if the number of electrode is less than 100, then we have to consider this corner electrodes capacitance in calculating capacitance. And the internal capacitance as can be derived by the equation as shown by C suffix I. So may I have the next box, sir, please? Okay. Now here we have found out this unit cell capacitance for the different geometry of the electrode structure. The unit cell capacitance, as it can be in this box, it is given by CE plus CS. It is nothing but the corner capacitance plus the electrode that is present adjacent to the corner electrode. And we can calculate the internal capacitance CII as shown in the formula. And similarly, we have the substrate capacitance CE. Overall corner capacitance can be derived from this CE. Now the expected change in the total capacitance will be the summation of two parameters. Mainly one is the response due to the dielectric change of the polymer, and another is the response due to the swelling of the analyte into the polymer, which can be seen by the del C. Del C is the capacitance change due to this dielectric response as well as the swelling of the polymer. Now, in the resultant discussion section, these are the tables for unit cell capacitance measurement. In table 2, it shows the unit cell capacitance one considering the corner electrode, and the second part, the second last three columns, it represents the capacitance for the internal considering the corner effect, that is, or you can say the aging effect. Now the same it is represented 4 and 5, which shows a gradual decrease in capacitance, unit cell capacitance value with the increase in the gap between the two electrodes. Gap in this case we have taken it as from 1 to 5 in the range of 0.5 micrometer, in the interval of 0.5 micrometer. So the figure 4 and 5, it represents the values of the capacitance of the unit cell structure. Now table 2, in table 2, this table 2 is considering the polymer structure, and table 3 is considering the polystyrene divinyl benzene, actually the polymer which is used mainly for the analyte limonene. Okay, I have used one model analyte, that is limonene, to observe the capacitance change in the overall capacitance structure.
Sorry to interfere, sir.
So,
sorry to interfere.
Hello.
Only 5 minutes is given, so you please hurry up, sir.
Hello. I'm not getting.
Sorry to interfere. I'm sorry to interfere you. Please hurry up, sir. The 5 minutes is over.
Okay. Sir, can I see this next portion, sir, in the topmost right? The curve that is shown in figure 8 and 9, it shows the partial change in the capacitance del C with respect to the dielectric change of the polymer layer as well as the thickness of the layer, because when this polymer layer absorb this analyte, it not only change the dielectric, it also swell up the polymer. So the del C, it represents both the changes actually. So figure 8 and figure 9, it represents the del C with respect to this dielectric and the height of the polymer layer. So can I go to the conclusion part, sir, please? Okay. So this interdigital sensor have been simulated showing a strong dependence of this capacitive response with the dielectric as well as the geometrical parameters. Now the effect of the sensor geometry parameters on the sensor performance, and definitely from the equation, first equation, it can be seen that this capacitance is directly proportional to the number of digit and also to the length of this electrostructure. So the analytic equations have been given for the design purpose and also for the optimization purpose. Thank you, sir. And these are some of the references.
Thank you, sir. Sir, any queries or anything people can ask? Amit, sir?
No, let's move to the next. Thank you.
Okay, thank you, sir.
Sir.
Next presentation by Chakravarti.
However, we have
Can you be a bit louder? I cannot hear you. Hi, hello, Bhashwati. Can you be a bit louder?
Ma'am, you're not audible.
Sir, can you hear me now?
Can you use a earphone with a mic? Probably you are using a phone, so please use a mic and an earphone, so it will be then audible.
Sir, I'm using earphone, but
Yeah, now
I
it's
don't.
fine. Now it's fine. Now it's fine. Go ahead.
Sir. Am I audible now?
Yes, go ahead.
Okay. So my topic I have already told. This particular CA-based detection has already performed by several groups using paper-based platforms and flexible medium as well. But those platforms lack limit of detection issues. To tackle that limit of detection issues, several methods have been implemented, like nanostructure-based substrate modifications and all. But those also have reached saturation right nowadays. So in this particular presentation, we have focused on enhancing the mass transport of the analyte towards the sensor detection to the application of applying electric field. Hello? Am I audible? Hello?
Yes, ma'am, you are audible, ma'am.
Okay. In this particular work, we have used a flexible PET substrate with screen printed electrode for POC applications. Additionally, we have also implemented CV characterization as well as EIS spectroscopy characterization for the effective detection of CA. And last of all, a portable potentiostat along with has already also been integrated in this particular work. Now, let's come to the fabrication part. For the fabrication of the screen printed electrode based platforms, we have used several inks like silver ink, carbon ink, and all. Hello? Sir, am I
You
audible?
don't. Yes, you are audible. You don't stop. There is some background, so you keep on telling. We are listening to you. Okay, don't stop. Yeah.
Okay, sir. In this particular substrate, we have first fabricated the screen printed electrodes using silver ink. After that, we have used carbon ink on top of the silver layer, and on top of the carbon layer, we have printed insulating ink for the fabrication of this screen printed electrode. After that, anodization has been also done about 20 seconds at 1.2 volt potential. This working electrode has two parts. This working electrode will be shorted for the electrochemical measurement technique, and this electrochemical measurement technique will incorporate graphene based on dielectrophoresis method. We have used dielectrophoresis method for the fabrication of graphene on top of the screen printed electrode. For that, we have applied a 19.5 volt peak-to-peak sinusoidal potential for 60 seconds of time. And on top of that, ZNO seed layer has been grown. For that, we have used sol gel technique. After that, ZNO nanorods have been fabricated using hydrothermal method. And we can see directional growth of ZNO nanorods in that particular setup. After fabricating all the things, we have functionalized the substrate. For the functionation process, we have incorporated two main methods. One is the cross-linking process, and another one is the salinization process. For the salinization process, we have used MTS, ethanol, and DI water. And for the cross-linking process, we have used GMBS solution. After doing all these things, the substrate is finally ready for the aptamer functionalization as well as the CEA functionalization. After that, their characterization part, we have done several characterization here. As we can see, the first image is the same image of screen printed electrode, which we can see here. It is a kind of rough surface as the molecules are attached to this particular surface. After that, we can see the same image of ZNO nanorods, which have been uniformly developed with surface packing density on graphene surface. And after that, we can see the XRD pattern of graphene, a layer of refraction peak centered around 2 of 25 degrees and 25 degree can be observed here. Along with that, we can see several peaks around 30 degree to 60 degree to theta value. This is because of the hexagonal Wurtzite structure of the ZNO with lattice constant around A, which is equals to 0.325 nanometer, and C, which is equals to 0.521 nanometer, like that. So we can also see that there is a same image of the sensor surface after immobilizing of the CA molecule. Here we can actually see, note that the nanorods openings have been blocked after the CA attachment. Finally, we can come to the result and discussion part. The results which we have already shown here depicts the CV characteristics of the particular sensor after and before application of electric field. First image which we can see, it is the without electric field representation of the sensing curve. Here we can see that after the immobilization of CA molecule, the curves have been deteriorated. This is because of the hindrance in the flow of electron from solution to electrode through the ZNO graphene heterojunction. But this hindrance gets over once we apply electric field in this particular sensor. We have applied several intensity electric fields like 0.5 volt, 0.8 volt, 1.2 volt and all. We have come to know by experiment that 0.8 and 1.2 volt, these two values actually gives us the best sensitivity results. Now, we have used this 0.8 volt intensity to finally analyze the particular structure for CEA immobilization using EIS technique, which we can see here from the graph. Now, this is a Nyquist plot. This Nyquist plot, when we actually summarize this, we have used one model. That model consists of several parameters like RSOL, RCT, RAG, etc. This RSOL is the solution resistance. Hello?
Yeah, can you quickly wind up, go to your main result and then conclusion?
Yes, sir. Yes, sir. And this parameters actually change when we change the concentration of the CEA molecule. So here we can see that not only the percentage change of RCT impacts the CEA detection, but also the percentage change in RAG and RSOL also impact in the CEA detection as well. Here we can also study the selectivity of the sensor using thrombin, BSA, PSA, these concentrations of 1 nanogram per ml solution. We have shown this using a Nyquist plot. Here we can clearly see that CEA detection has got the best result apart from the other molecules. Finally, we have done the smartphone application part. The unknown solution has been dropped on the screen printed sensor surface, and then the interfaced potentiostat, which then allows for the capture of CA under the influence of electric field and computes the percentage change in RCT, RAG, and RSOL. Then the finally apps collect those data and it calibrate those functional data, and it gives us the result, mean result, the CEA concentration. This concentration we have also validated with the gold standard, and we have come to know that it agrees well with the gold standard as well. So this is my work so far. And there are some references as well. Thank you.
Yeah, so Bhaswati, I have one question. So
Yes,
you have mentioned limit of detection as 1 femtogram per ml, and your range is, this is a dynamic range if I understand correctly, 1
Yes, sir.
femtogram to 10 picogram. So
Yes,
what
sir.
happens beyond this concentration? If you further increase concentration beyond 10 picogram per ml, what happens?
We haven't done taking other considerations. We have already limited our considerations to that particular level.
Okay, so this is not dynamic range. So this is the range where you have measured.
Yes, sir. We have measured.
And how you determine the limit of detection? Can you define a
Sir,
basic question?
beyond this 1 femtogram per ml, the curve gets deteriorated so badly that we couldn't understand the differentiation between lower concentration ranges. So up to 1 femtogram per ml, we can actually precisely decide that this concentration can be measured.
Okay, thank you.
Okay, welcome.
Next.
Next presentation. Thank you. Hello, Nidhi ma'am, are you there?
Yeah, can I start?
Yes, ma'am, you start.
Very good afternoon to all. The title of my presentation is Paper-Based Electrochemical Biosensor for E. coli O157F7 detection. Even in the era of global urbanization, around 55% population of the developing countries such as ours still reside in rural areas. And such people have limited access to basic necessities like even clean drinking water. So they are highly susceptible to pathogenic infections. And the proper diagnostic tools are not available to such people because of a major factor of the cost. Thus, in the present work, we propose a paper-based electrochemical biosensor Paper is easily accessible, inexpensive, biodegradable, and flexible. And a pathogenic strain of E. coli, that is O157F7, has been chosen as the test analyte in the present work. As can be observed in the poster, this strain can cause severe illnesses in the humans, ranging from bloody diarrhea to kidney failure. Thus, paper-based analytical devices, commonly known as pads, have been devised for such a pathogenic strain. Starting from the laboratory available Whatman filter paper, we prepared the working and counter electrodes using a simple pencil and the reference electrode using a silver paste. The counter electrode and working electrodes were further filled with graphite ink for improving their conduction. Then a hydrophobic boundary to confine the sample in the sample zone was designed using a glue gun. And the final device thus consisted of a sample zone, also known as the detection zone, of a diameter 1 centimeter, surrounded by a hydrophobic boundary and a buffer zone. Thus, overall, the size of this device was around 3 by 3 centimeter. The electrodes were then directly connected to the measurement setup. The measurements were recorded using a Gamry electrochemical analyzer. For that, firstly, the E. coli antibody were immobilized over the detection zone by simply drop casting and leaving for around 30 minutes in an incubator at 27 degrees Celsius. Then the CV curve, as can be observed in the cyclic voltammetric curves. So can you please move the poster down? Yeah, as can be observed in the CV curves for E. coli detection, there was a significant decrease in the presence of E. coli AB in the current, and the current further decreased when any concentration of E. coli cells was brought in contact with the antibodies. Thus, for measuring the response, chronoemperimetric studies were performed in the E. coli by varying the E. coli in the range of 10 to the power 2 to 10 to the power 10 cells per ml. And it can be observed that the response came out to be linear in this range, and with the deviation of less than 5% was observed. Thus, the results, as stated in the results, the linear range of the device platform was found to be 10 to the power 2 to 10 to the power 10 cells per ml, and with a limit of detection of 5 cells per ml. Thus, it can be concluded that the measurements on paper substrate for E. coli O157H7 have turned out to be highly promising for development of paper-based point-of-care diagnostic tools, which are both economical and easily accessible to a wide range of population all over the world. Thank you.
Okay, thank you, Nidhi. So I have one question, like how have you determined the specificity of your sensor?
Sir, not using the paper-based platform, but similar work I have done on an thin film-based platform. Over that, I have checked the specificity. And also, since we are dealing with E. coli specific antibodies, we can say that it will be specific in this case also.
But you are not washing your things, right? Are you washing after adding your
Sir,
E.
the
coli
thing is
cells?
paper-based platform is not reusable.
No, my question is that if you have a mixture or you don't know whether it's an E. coli or something else, if you add there, maybe that itself, the bacteria itself can give a signal.
Yeah.
Even if it is E. coli or not. So that has to be checked.
Yeah, so that we are washing after immobilizing the E. coli cells over the antibody, we are washing it with buffer thrice, then taking the measurements.
Okay, okay, thank you.
Okay, sir.
Hello.
Yes, ma'am. You can present now.
Am I audible? Can I start?
Yes, ma'am.
Yeah. Good evening, everyone. So today I'm going to be discussing the evaluation of a miniaturized NIR spectrometer for estimating total curcuminoids in powdered turmeric samples. So to give a quick background, a growing demand for this on-site quality analysis where we require faster results to analyze the quality. We have thought of an NIR spectrometer to do so. So what happens traditionally is that any material that needs to be tested is taken to the lab, and it takes a lot of time for the results to come back, and a lot of the procedure is halted and it's time consuming. So if we have a spectrometer or a device that can be used remotely to give us results, this will help us a lot in taking on-site decisions faster. So a lot of areas in the food and the agricultural industries have used these portable spectrometers, but today I'll be talking about the use of a commercial spectrometer to quantify an active ingredient called curcumin in turmeric powdered samples. So why turmeric as such? So turmeric has been used in the household industries, and it has a lot of benefits. And in figure 1 you can see curcumin, that's the active ingredient. It is considered an antibacterial, antifungal and anti-cancerous thing. So it's considered a very potent product in the market. So the for the procedure, for what we have done is we have taken turmeric and quantified curcumin using HPLC. So HPLC is a standard method where we chemically analyze, and we know for sure curcumin present in a particular amount of turmeric sample. So we have used an NIR spectrometer called SIO that is commercially available under the name Consumer Physics. So we have taken these powders, we have sieved it with a 250 micron sieve and placed in a rectangular blocks, and we have put the device on top of it to scan. So this spectrometer scans in the range of 740 to 1050 nanometers. So that is in the close NIR range. So NIR range, to give a small introduction, it captures the chemical signal through the vibrational spectroscopy. As the experimental setup, you can see the device is placed on the powder, and then we take 30 scans per sample to analyze for better averaging. Combined with machine learning, we take the spectra and subjected to pre-processing. So this SIO has a cloud-based software, and it offers a set of pre-processing steps. So this set of pre-processing is not, there's no hard and fast rule as what to be used, what kind of methods works for different kinds of data. So we have scatter correction. So scatter correction basically takes care of the multiplicative and the additional scattering that is caused while capturing the spectra. Spectral derivatives is used to hello.
Yes, you are audible. Please go ahead.
I am audible, right? Okay, because I didn't get any response. Okay, all right. So I was talking about spectral derivatives. So we've used the Savitzky-Golay filter for second derivative filter to extract features that are not visible in the diffuse reflectance mode. So a couple of these pre-processing were tried with a trial and error method to see what works best. So after the pre-processing step, this entire thing was subjected to PLSR. So PLSR is a partial least square regression algorithm that that takes the spectra, and then we have a metadata that is our HPLC data, and it correlates the spectra and the metadata to throw a model. And the model performance is evaluated with two parameters. One is R square, that is a coefficient of determination, and RMSE, that is a root mean square error. So among all of the pre-processing steps we have tried for this data, the combination of SNV, that is standard normal variate, which is a scatter correction filter, and a Savitzky-Golay filter give us the best R square of 0.797 and the least RMSE of 0.306. So we used this model to test data or test samples that have not been used on the in the training model. So the training model consisted of 31 samples, and we tested this model on 6 test samples that have not been used. So as you can see, we achieved a high R square of 0.93, and the error bar represents the deviation among 10 scans. So we just don't take one scan and we throw out an error and we throw out the result. We take 10 scans and we average them out. So the error between these predictions are between 5 to 25%, and the more samples we add to the training data, and the more the model is going to improve. So in conclusion, this study shows experimental proof for how we can practically use commercialized spectrometers to evaluate different active ingredients in different spices. Also, our lab is in IISc. We have also are developing our own spectrometers with off-the-shelf components, and we're using that to measure turmeric as well. So to expand this, our idea is to measure or quantify as many active ingredients as possible in an assortment of spices, so that we can develop a model system to make faster decisions on an on-site analysis. That's it from my side. Thank you.
Thank you, Ansika. Now, I have one question: that how are you going to distinguish between different analytes if you have a mixture of like curcumin with others? So using your technique, how are you going to do that? So have you performed any experiments related to this? And I would like to say that, go ahead.
Yeah, so every molecule or every ingredient has a very specific chemical signature. So like if I take curcumin and something else, if I scan it, even in the raw spectra, it can be seen that the signature is very different.
So which signature are you talking about? The NIR absorption?
The NIR signature. So all of the measurements are done in diffuse reflectance mode, but these can be converted to absorbance equivalents using an equation called the Kubleka-Monk equation. That is very well described in literature, so that we can do absorbance equivalents to that.
No, that is fine, but the thing is that the diffuse reflectance which you are measuring, so there will be a lot of molecules which will have similar signature. Like it's not a very it's not a kind of Raman signature which is like specific for a particular molecule. So what is your plan? How are you going to distinguish that?
So the idea is actually not to distinguish it just based on the signature we get. So the idea is we capture the signature and we correlate it to the amount of curcumin that we have got from the sample. So it's a correlation process and not just base identification or just looking at the spectra.
Okay, thank you.
Yeah, thank you.
Krishnapriya ma'am.
Hello, sir. Am I audible?
Yes, ma'am. You can start.
Okay. Good evening to everyone. Title of my presentation is Carbon Quantum Dots for Biosensors, an investigation on the optical properties. So these carbon quantum dots are the zero-dimensional nanostructures of carbon, and it is gaining wide attention since its accidental discovery in 2004. There are a variety of applications including optoelectronics, photovoltaics, photocatalysis, bioimaging, and biosensing. And we are focusing here on the biosensing application. And here we can see the luminescent different applications of luminescent carbon quantum dots and the properties of CQDs, which make it a highly highly effective for bio applications, such as a reasonable PL, high resistance to photo bleaching, high aqueous solubility, excellent biocompatibility, and low toxicity, and also the chemical inertness. Now coming to the synthesis part, can you just scroll it down? We have done the hydrothermal synthesis of CQDs using citric acid and ethylene diamine as the precursors. Citric acid is used as the highly reactive carbon source, and ethylene diamine was used as the nitrogen dopant material. Actually, this nitrogen doping is done to enhance the quantum yield of CQDs prepared, and the reaction temperature and reaction time was varied from 100 degrees Celsius to 200 degrees Celsius with a difference of 25 degrees Celsius, and reaction time was varied as 6 hour, 5 hour, 3 hour and 1 hour. And the resultant solution was dialyzed for 24 hours, and the CQDs, you can see the visible luminescence of CQDs in the bottom part. Now coming to the characterization, Figure 1 shows the XRD pattern of CQDs obtained. You can see a broad diffraction peak at 2 theta is equal to 24 degree corresponding to the amorphous nature of NCQDs. And figure 2 shows the TEM image of NCQDs prepared at two different time duration and at 200 degrees Celsius. From the TEM image, it is clear that as the time increases, the size of the nanoparticles shows a slight increase due to the agglomeration of nanoparticles formed with increase in time. And the figure 3 shows the photoluminescence behavior of CQDs. Here, the CQDs prepared shows a excitation dependent emission behavior due to the non-uniform nature of surface, non-uniform surface nature of CQDs. And also we can see a red shift in emission as the excitation wavelength increases. And figure 4 shows the UV visible absorption spectra of NCQDs prepared at constant temperature and at a different time duration. And in all the at a temperature 200 degrees Celsius, by varying the reaction temperature, we got the same absorption peaks. A shoulder absorption peak at approximately 238 nanometer corresponding to the pi star transition of aromatic sp2 domains, and a strong absorption peak at 348 nanometer corresponding to the n pi star transition of C double bond O or C double bond N group. And on looking at B, figure 4B, as the temperature, as we changed the temperature, the result was different. The same peaks were observed only for only at the condition 175 degrees Celsius and 1 hour, and on decreasing the temperature further, the peak was absent. That means even though CQDs formed, it was not up to the concentration as that increased temperature. And as a conclusion, we can say that water-soluble NCQDs were synthesized through cost-effective single-step hydrothermal method by varying the growth time and temperature. And the investigation proves that reaction temperature is more influential than the reaction time on the production of NCQDs. And we can use this synthesized CQDs as a biosensor, for example, for detecting the hemoglobin, since the absorption range of hemoglobin matches with the emission range of CQDs, and we can use that for sensing applications. Thank you.
Thank you, Krishna Priya. So you are a PhD, right?
Yes, sir.
So I would like to know that I don't see any novelty in the work which you have presented. So these are all reported. So can you just specify like what are you planning to do with this? Because whatever you have presented is already in literature.
Sir, actually, this variation in temperature and time, we tried to optimize the reaction conditions to a lower temperature and lower time, and then use that for sensing application.
So what advantage will you get? But what will you gain from that there?
By simplifying the making procedure, I think we can get a better result.
Okay. Okay, thank you.
Okay, sir.
Manika Jha. Next presenter. Manika Jha, are you there? Manika Jha. आवाज आ रही है? Amit sir?
Yeah,
Sir?
I think
Sir?
she's not online probably. Sure.
Okay, sir. Can we move on to next person?
Yeah, sure. Please go ahead.
Yes. Thank you, sir. Henam Sylvia Devi?
Yes, I'm here. Am I audible?
Yes, ma'am, you're audible. So you can start.
Okay. Good afternoon, everyone. I'm Hanam Sadvadevi. I will be discussing about the interaction of glucose with copper oxide, which can be a future platform for sensing glucose. If we know that diabetes is one of the major diseases that we are facing, and it is a metabolic disorder when our body is unable to regulate the level of the glucose in the blood. And in a diabetic patient, this condition result in a low blood pressure, sugar. So, we would like to present some material here, the possible device that can help us detect the minimum level of the glucose in the future. And the device and material that we develop should be very stable, and then it should be for long term and cost effective. That's what the aim of the the work is. So we have sent it, can you scroll it down to the introduction and method part? We have tried to synthesize the copper oxide metal, copper oxide nanomaterial. And in literature, many people have used the silver dot with the graphene, gold, nickel as well. And even when they come to the nanoscale nickel, gold, they lead to the accumulation inside the body, and creating become toxic. Even the silver also. So we prefer to use the copper oxide instead of using the metal nanoparticles. And even those compared to the novel metal, they are very cheap. So we have decided to synthesize copper oxide, that too in such a way that it remains stable for more than 6 months, for years, and they remain without precipitating out in the solution. So we synthesize it using ionic liquid that we term it as diphoric solvent, or DES. This solvent is an ionic liquid which make the solvent conductive, and if we abstract the the metal copper oxide from it, it remains stable in the alcohol or water for more than 6 to 7 months without any precipitation and in a dispersed form. And we have synthesized it using the choline chloride, gallic acid, and ethylene glycol at 80 degrees centigrade. And we achieved the copper oxide. And in the characterization part, can you
Hello, Henam, you're not audible. You're muted.
Am I
Yeah.
audible now? Okay. Sorry. Okay, from the excited we confirm the formation of copper oxide nanoparticle. And then from the term we have determined the size of the particle to be 58 nanometer. Can you scroll it down after the, yeah. And the EDS confirmed the presence of copper and then oxygen in 1:1 atomic ratio, which is nearly to be the copper oxide only. And what technique that we want to use for sensing the glucose is the photoluminescence property of the copper oxide that we studied in this. We have excited the copper oxide, this film. We have deposited a film of the copper oxide on a glass substrate, and then we have excited this thickness of the film is 1.6 micrometer. And when we excite it at 325 nanometer, we get an emission at around 341 nanometer, and then which is because of the exciton recombination, and then peak at 4 times, and as well as at the 561 and the 664 emission when excited at the 325. This emission, we can see at the figure number 4. The black color is of copper oxide, and when we like coated area, when we put the glucose of 10 to the power minus 3 mole millimolar, 1 millimolar, the PL like increases 60-fold time, and then it is within the time period of 5 minutes only. The red one is for after after coated with glucose, yeah, after putting the glucose on that thin film. And then with time, this PL emission started degrading, like it is given 15 to 30, which may be the like this enhancement in the glucose, like PL may be because of the oxidative like oxidation of the glucose on the surface of the copper oxide by transferring the electron to the copper, which result in the enhancement of the PL. And then with time, it started degrading. And this mechanism is because of the oxidation of the glucose to the glucolectone and to the gluconic acid. So this initial work gave us a hint that we can generate the copper oxide device based on this study to detect the diabetes, like having low sugar level of 1.1 to 20.08 millimolar. And this is the work that I have done so far in this field, and some reference are given here. Thank you.
Henam, thank you. So I would like to know that for glucose sensing here, in your case, you need a spectrophotometer to analyze the presence of glucose, right?
Photoluminance.
Photoluminance, yeah. So can you convert your system to a kind of visual, like naked eye detection with integration or something? Because nowadays sensors are available where you don't need to use any spectrophotometer or any photoluminescence device.
Yeah, I understand that. We can
like visual color detection or visual color generation, like peroxidase activity of different nanomaterial. So what do you think?
Yeah, we are trying that. We are expecting it can be, if it is visible to our eyes, then it will be of a great achievement, but we are trying our best to do so.
And you have used only one concentration for monitoring, right?
Yes, I have tried with 10 to the power minus 4 and 10 to the power minus 2 also. As predicted, with increase in the concentration of the glucose, the intensity do increase. But we have do the extensive study on 10 to the power minus 3 only.
Okay, thank you.
Thank you.
The next presenter is Sneha M. Ma'am, are you there? Sir, I think the Sneha ma'am is not there online.
Okay, so let us move to the next.
Yes, sir. Hema ma'am, are you there? Hema ma'am?
Can you hear me?
Yeah, yes ma'am, yes ma'am. Now you can present, ma'am.
Okay. I'm Hema from Bharat Institute of Higher Education and Research. My title is Augmented Reality on User-Friendly Maneuver for Hunting Arsenic Toxicant. Pollution or contamination plays a major part in dreadful health hazard. Water, the most essential entity, is being consumed without the knowledge of contaminants.
Whenever there is a talk for purification of water, arsenic contamination level must also be considered, which is being neglected in practice. Though there are many pollutants in seawater, arsenic is the major geogenic and toxic pollutant producing health threat like lung cancer, skin cancer, or cardiovascular diseases. The standard methods of quantitative analysis cannot be applied to seawater without adequate checks on their accuracy. Problem domains are bulky, not user friendly, and we need laboratory to detect the data and all. So there is a system need, user friendly, accurate. So my system is PAMSOT, Portable Automated Monitoring System for Arsenic Toxicant. The system is integrated with GPS and GSM. My data is communicated for online monitoring. This is the transmitter model and this one is the receiver module. Please down. Please scroll down. This side, this part. This is the online monitoring system. This is the front and back end system. Here, that side, sir. This one is the fabricated strip. This one is fabricated screen printer strip in SECRI, Central Electrochemical Research Institute. The strip is under test. And this side, sir, this side, please. Up. That's the fabricated strip is tested for various metals also with DPV, differential pulse photometry. I tested cadmium, lead, copper, silver, gold also for the same sensor strip. And this one is the correlated. Hello, my fabricated strip is the test data is tested with photometric method also for correlation test. I got 0.996 correlation analysis. Then this one, please, this side, sir. After the contamination level is sent to remote end, if the contamination level is within the range, our screen becomes blue, and if it is beyond the limit, it becomes red. For that MCL by WHO, that is World Health Organization, the maximum contamination level of arsenic is 10 micrograms per liter, that is 10 ppb. If this is the within the limit, the screen becomes blue, and if it is beyond the limit, it becomes red. Then finally, for the future enhancement of, that is lab on chip, the same fabricated strip is tested for some gold, silver, mercury, bismuth, cadmium, etc. So if the deposition potential is varied for each and every metals, the same device could be detect the many pollutants at a time. Hello, sir, can hear me?
Yes, completed. Yeah, we can hear you.
So this is the transmitter module. This is the receiver module. This one is the my fabricated strip I tested with the standard method of photometric method. Correlation I got. This one for online monitoring. This is the front end screen and back end screen. For the future, that is ongoing project I'm doing for the same strip for bulk metal pollutants, different bulk metal pollutants. For arsenic, I optimize the value of deposit potential is 0.3 volts, sir. Can sir, this side? This. Okay, sir. That is the optimize the deposit potential for arsenic alone is 0.3 volts. For that, each and every metals there is a deposit potential. The technique used is ASV, anodic stripping voltammetry, sir. ASV is a technique where The metal ion of interest is pre-concentrated in an anodic metal, then which is stripped away from the metal surface with with reverse potential, sir. I'll repeat again. ASV is a technique where the metal ion of interest is to be pre-concentrated on an anode with suitable deposition potential, then stripped away from the surface by using anodic potential sweep. The stripped away electrons is nothing but flow of electrons, which is current. So this side, sir, can move that side, sir, that side, fourth column, up, a bit up. So for the linearity test, sorry, I couldn't have the diagrams at that side. Control namakilla. Sir, I concluded that. Hello.
Yeah, please conclude.
The contamination level of the arsenic varies. The corresponding current level also increases. What I'm saying is each and every nanoparticle of the arsenic we are detecting, sir. So our system is more accurate than the standard system, sir.
Okay, thank you. So can you please let us know about the cost of your system?
Sir, let us see the front, sir. I saw the fabricated strip missing also for you. This one. Just a minute, sir. This is the strip under test, and within 35 strips can be fabricated within 10 minutes, and the strip would be 100 rupees only, sir. This is the minimum cost, but we have to buy the costly ink from Singapore and all.
Okay, thank you. Thank you very much.
Thank you, sir. Time is limited. That is what I couldn't
No, it was a good presentation. Thank you.
Okay, thank you, sir. Any other questions, sir? Sir, can I tell some more?
I'm fine. No, you're done. Thank you.
Okay, thank you, sir. Thank you so much. Sir, what about e-certificate? I have to fill the any form?
That we will say, we will let you know later, ma'am.
Thank you, sir. Thank you so much. Thank you for giving me opportunity, sir.
So, Senthil, is it done, right?
Sir?
No. You can. I'm not talking to you.
Okay, sir. Thank you, sir. Thank you so much.
Sir, the two names are left out. That is Manika Jha and Sneha. If there are there, any one of them, you can present. Sir?
So are they back? Manika, are you present? I don't think so. What is the duration? Like, what was the end time for this presentation?
It was 3:30 to 5 o'clock, sir.
Okay.
1.5 hours for the poster sessions.
Okay. Sneha M.
Yes,
Is she back? Are you back?
yes,
Okay, so can you present? Sneha is back. Senthil, so you can put her poster.
Yes. Sneha ma'am, you can present now.
Yes, sir. Hello all, this is Neha. We report on a type of organic electrochemical transistor called
Sneha, sorry for disturbing you. Can you please speak louder or keep your microphone close to your mouth? Your voice is not audible.
Is this better, sir?
I'm sorry.
Better?
No.
No, sir.
No,
Hello?
it's same. Yeah.
Oh, it's still the same, sir.
Yeah, so you have to speak a bit louder.
Actually, internet issues because of the cyclone, sir.
Okay, okay. Okay, go ahead.
Uh, uh, is it better now, sir? The voice? Hello?
Yes, go ahead, go ahead.
So we report on a type of organic electrochemical transistor called biorestor. Uh, this is to monitor drought stress and salinity stress in plants, especially crop plants. So the motive of the sensor is agriculture application, precision agriculture. So drought stress and salinity stress are two most important abiotic stresses on crop plants. Abiotic stress is nothing but negative impact of non-living factors on living organisms. Sir, am I audible clearly?
Yes, you are audible.
So abiotic stress is negative impact of non-living factors on living organisms in a specific environment. So on plants, drought stress and salinity stress are two most important abiotic stresses. So the purpose of this sensor is to monitor drought stress and salinity stress in crop plants because of these because these two stresses detrimentally affect crop yields worldwide. So the application of the sensor is in precision agriculture. Biorista, the name of the sensor is Biorista, and it's a type of organic electrochemical transistor. It's developed on cotton thread with plant sap acting as the electrolyte. Uh, this is a biomimetic sensor. It behaves as part the plant. So the key parts of the bioreactor are plant sap, which acts as electrolyte, and there is a cotton thread, which is functionalized with the
Hello? Sneha, you're not audible.
I think some internet connection problems.
Okay.
Can wait for 2 minutes or you can end the session?
Yeah, sure. At 5 o'clock we can, in 5 minutes I can wait. We can.
Okay. Yes, sir, we'll wait for 2 minutes. If it is not, then we'll end the sessions.
Sure.
Yes. Thank you, sir. Thank you so much.
You're welcome.
Hello, sir. Sir, Professor Amit sir?
Yes, yes.
Sir, we can end the session, sir. I think there's a technical
Okay.
problem for the.
Okay, fine. Okay, sure.
Yes,
Okay,
sir.
good luck.
Yes,
See
sir.
you.
Thank you everyone for attending the session, and we thank Amit sir for passion word listening and sharing this session. Right now we will end this session, and 5 o'clock another talk is there in hall 6. The participants can move on to the other section. Thank you, Amit sir, for your valuable time.
Thank you. Bye.
Thank you.
Hello, sir. Hello, sir. Hello. 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 Binet?